My name is Matt Eichenfield. We're having a few technical difficulties with the AV in the room, so just give us a couple of minutes. We'll get this fixed, and then we will start. Okay, we have fixed the AV, and let's see. So I guess let's start by introducing everyone that's going to be presenting today. So my name is Matt Eichenfield. I'm a professor here in the College of Optical Sciences at University of Arizona. I'm also a joint appointee at Sandia National Labs, where I also work and do research. And I am the PI, and along with Saikat Guha, the co-director of the Center for Quantum Networks. So my colleagues here and I are going to be presenting to you today on quantum network integrated devices and systems. That's a fairly broad title. We'll get into more about what we're going to be actually presenting. Or Shelby will jump the gun and start now. But let's introduce everybody else.
I'm Shelby Jenkins. I'm currently a postdoc in the ECE department. My background is in integrated devices and magneto-optics, and now I work in analytical quantum network models.
I'm Eileen. I'm one of Matt's grad students here at the University of Arizona, and I'll be talking later about what I'm doing.
I'm Jake. I'm also a grad student in Matt's group, and I'll be talking about integrated photonic devices.
Yeah, so the format here, so I'll give a little introduction. Then Shelby is going to give a longer technical presentation. She'll turn it back to me. I'll do some more. And then in the end of the course, I thought it would be good, useful, instructive for you guys to see presentations from my graduate students on some more technical aspects of what we actually do, in part because they're the ones doing the actual work in the lab, and they can give you really deep insight into the kinds of things that they're working on. And I think it's good also for people in the audience. Presumably not everybody in the audience is an expert. Many of you are students. And Jake and Eileen are, correct me if I'm wrong, third and second year graduate students. And so, these are people who just a few years ago were probably in the same position that you are in now. And so I think it's really cool to be able to see, with just a few years of PhD training after their bachelor's degrees, kind of what you might be capable of working on and doing in just a few years. So I thought that would be a nice addition to, just the presentations and content. So that will be the format for the day. We'll probably take a few breaks, just short ones in the middle, both for the instructors and for you all to be able to, take bio breaks or whatever you'd like to do, get some food. I have been told that the way this will work, so I can type into the webinar chat to ask questions. Unfortunately, your mics are not enabled, so you can't respond to my questions verbally, but I will probably at various points, or the other folks here will type some questions into the chat and also verbalize them. And then it'd be nice to be able to get your answers. And don't use ChatGPT, because that's cheating. Or Google. We would like to just see if people sort of know. A lot of these things will be sort of checking in with, whether you're understanding things and that sort. And then some might just be sort of, hey, does anybody know what this is? So, okay. So with that, I think we'll get started. So I'm going to start off with just a short introduction. First, I will disable notifications on my laptop. Okay, and then I need to share.
Oh, I'm watching.
No, I'll just share over you. Oh boy. What? Again? Okay. Oh, you don't see that? Oh, let me stop the share. There's this option that it gives you now when you share to sort of have like multiple shares. So I'm not replacing yours. I'm just,
I can just reach.
that's okay. Do you guys see it now? Well, shucks. Share the window. Okay. Share. How do you guys see it? Okay. Wow, that's the wrong presentation. So, oh boy. There we go. That is the right presentation that is up currently. Except now that it's switched to the wrong one. This is really annoying. Sorry, folks. Give me a minute here. I'm gonna close. Well, or maybe I need to shift it to the other screen or something.
Only matters if they can see it on Zoom.
Are you trying to show the documents?
Yeah. And then, so like this is the one. Click that. Yeah, I mean, I said to share this. That's what my screen sees. You see that on Zoom? Oh, okay. Well then, but then when I go into, oh, that's why I was pressing the wrong screen's presenter mode. Okay. Now you guys see that? Okay, great. Okay, so we're gonna talk a little bit about Diamond. Obviously the Center for Quantum Networks is very aptly named, right? We're trying to develop the full stack of technologies and theory necessary to understand and build scalable quantum networks. And one of the key elements of quantum networks is the ability to produce entanglement. And we're not going to get too deep into entanglement because of the way that we set the course up and the prerequisites. What we're going to say is that entanglement is a way of producing perfect correlations. Well, it doesn't have to be perfect, but you can produce up to essentially perfect correlations between quantum objects that allow you to essentially connect things together in ways that measurements on one object that are entangled with another instantaneously affect the other. Okay, and the reason that that's important is because that is the way that you actually are able to distribute quantum information across a network. Now, the entanglement is not used to transmit information. You're generally making measurements of quantum states that you don't know what they are. And so you're not transmitting information. This is not faster than light communication. This is the fact that I have pre-established some quantum link between two objects or many objects. And when I do something to the one over here, it instantaneously affects what is going on with the one, over somewhere else, that's entangled with it. But I can't actually communicate with that, right? In other words, I don't know what the outcome is when I make this measurement over here. I do something to it. I interact with this system and it changes what's going on in the system over there, but I can't do it in a way that allows me to actually transmit information. All it allows me to do is have them be connected together coherently. And that's really what we're trying to do in a network, right? We want to be able to, for example, I have a quantum computer at node A, and it's say operating independently to start. If I can connect it to a quantum computer at node B, one of the things that you can do is you can make that thing behave as though it is one larger quantum computer. But in order for that to work, it has to actually be entangled across that optical link, or across, it has to be entangled, period. One way to do that is with an optical link. So if they are entangled, if these two quantum processors are entangled with each other, then it will behave like a larger quantum processor. And alternatively, you can operate them independently where they're not entangled with each other. Then you can do computations, but the way that scales is exponentially slower than if you connect them together quantum mechanically. So another example is, maybe I have two sensors, and if I want those, I could just use those sensors independently and then communicate the results across some channel, or I can entangle them together. And then often what happens is that their sensitivity or the speed with which they can detect something will be enhanced by the fact that they are quantum mechanically entangled. So that's kind of what we want to try to do. And the physical systems that we need to be able to do that are pretty varied. But I'm going to kind of walk you through the properties that we would like to have for this to be able to work. And I'm going to use as the kind of canonical example here, these things that are called color centers in Diamond. And so we're talking, literally about diamond, like diamond rings, right? Diamond anvils, whatever. The same diamond that you all are used to. If you go and you buy a diamond ring, they're generally sorted and priced by their color. That color is, in fact, the same color that is given by the color centers we'll be talking about. So what it is that you have this kind of perfect carbon lattice, and that there can be defects in these carbon lattices where other atoms can covalently bond to the surrounding lattice. So if you have a defect where you have a nitrogen atom that is participating in this covalent interaction and inserted into the lattice, that's called nitrogen vacancy center, and it gives rise to the kind of yellow color that diamonds often have, right? You'll hear about yellow diamond. If the diamond has a reddish color, that would be from a silicon vacancy and so forth. So and also I guess tin is probably pretty red. But so these same defects in the lattice and these atoms that are doped essentially in the diamond and participating in these covalent interactions with the other carbon atoms, diamond is entirely made of carbon. Those things actually, they give it color, and they're also the ones that we use to create these, quantum networks, okay, or that we are attempting to use to make these quantum networks, okay? So let's talk about the properties of diamond. So this is, something I essentially just said, right? Implanting single atoms like silicon or tin in the lattice of carbon atoms in diamond can create something extraordinary. And that is a defect complex of the lattice with electrons that orbit that defect like an atom. So what does that mean? So I'm showing you here, this is this could either be silicon or tin. It's a certain kind of defect, but so this atom is sitting between, these blue are carbon atoms. There are missing carbon atoms here, and then this is replacing those missing carbon atoms. The the electrons from this dopant atom, in this case, like I said, either silicon or tin, actually orbit the defect here. So it looks like a positive charge that's sitting here stably bound, in the lattice, and it has excess electrons that will orbit it just like an electron would orbit, say, a hydrogen atom, or any other kind of atom. And the really amazing thing is that these electronic orbitals and the rest of the properties of that system are very much like an atom. So they have these optical transitions that, well, here, I think I've listed them. They make them ideal for quantum networking. What are these properties? So they have these optical transitions, meaning that if I give this little region in space a specific electromagnetic stimulation, meaning it has the right polarization of light, it has the right frequency or color of light, and perhaps the right direction, you can actually stimulate the electron in that defect complex to a higher energy level. And then just like an atom, when that excitation inevitably decays back into the ground state that it was originally in, it will emit a photon. Okay, and that's exactly what gives them the color, right? So if you have white light in a room and it's shining on your precious diamond ring, and it has a silicon or tin vacancy center somewhere in there, or more than likely many of them, some of the colors of the light in the white light that's illuminating the diamond will excite these things into their excited energy levels, and then when they decay back, they'll emit these red colored photons, and that's what'll give it sort of a reddish color. Okay, so that's property one. Now this one is a little bit deeper. So they have the ability to store quantum information in special 2-level systems, which we call qubits, for very long times. And the particular mechanism for that storage and the creation of that qubit is actually in a special kind of angular momentum of the electrons and neutrons. So I said before that we can envision an electron essentially orbiting this. I don't know if actually, yeah, I guess people can see my mouse, yeah. I guess I could use the laser pointer. Here. So you can imagine the electrons essentially orbiting this defect complex, right? That's called orbital angular momentum. Okay, but just like a planet orbiting a star, right, or a moon orbiting a planet, right? Let's talk about the moon, right? So the moon is orbiting planet Earth, right? And so it's orbiting around, but it's also spinning on its axis, right? Now, an electron is an elementary point particle, so we actually don't expect to be able to sort of observe it rotating around on its axis, but nevertheless, it has a property where it responds to magnetic fields, for example, in exactly the same way as though it were like a little sphere of charge rotating on its axis with essentially a current dipole. A magnetic field created by a current that gives it a dipole moment. So you can think of this thing as both orbiting around and also rotating on its axis. That rotation we call spin. Okay, and you may have heard of it if you have any familiarity with quantum mechanics. But so the electrons have spin. Also the nucleons have spin, right? So there are protons and neutrons in the nucleus of this tin or silicon atom, and they are all as well rotating on their axes essentially, and there's a net addition of angular momentum, right? Some of them point up, some of them point down, and you end up with a net angular momentum of the nuclear system as well. And so there's spin from the electrons and there's spin from the neutrons. Okay, so what I want to say here, and again, we don't want to get too deep into energy level diagrams, anything like that. So what I'll say is that the spin from the electron actually determines the energy of the electron if I put it in a magnetic field. And what that means is that I can get light to interact with that electron in such a way that it depends, whether or not the thing absorbs light or emits light can be made to depend on the spin degree of freedom of the electron. Okay, so that spin degree of freedom is essentially optically active. So that gives me a way to basically interact with that qubit, right, with light. So I can stimulate it in such a way to create a particular state of the electronic qubit. Okay. Now the nuclear spin is not optically active. Okay. So however, if I apply a magnetic field to this system, I can couple the electronic spin degree of freedom to the nuclear spin degree of freedom, and that allows them to interact with each other. So I can perform quantum operations between the electron and the neutron, and I can perform quantum operations between the electron and photons. Okay, so those properties together allow me to produce this entanglement, and we'll talk a little bit about how. But a couple little more properties that just are maybe they're the reason that we're choosing this system, or some more of the reasons we're choosing this particular system. The density of these things can be very high. So, for those of you who have heard about, for example, the amazing results from, say, Google and IBM making superconducting circuit qubits, for example, those superconducting circuit qubits are hundreds of microns on a side, if not millimeters on a side. And so, you can have a qubit approximately every millimeter, right? These qubits that we get by implanting atoms into diamond, you can have many of them in a square micron. So in essentially one millionth of the area, right? And the other one is roughly like a millimeter by a millimeter. You sort of fit one qubit. These, a micron by a micron, you can fit something like maybe 10, right? So it's millions of times higher qubit density. And in the end, that will matter, right? If you really want to pack a lot of qubits into a quantum processor, or in this case, when I say processor, we're really talking about the ability to sort of create massive entanglement, which I'll tell you about in another slide. But the ability to do that is it's dependent on your ability to have lots and lots of qubits that can coherently interact with each other. So it would seem, although there are lots of caveats to these things, but at first blush you would expect that it would be better to be able to have a higher qubit density, and to have millions of times higher qubit density would be a significant advantage, right? So that's one of the reasons that we choose Diamond for this Center for Quantum Networks approach. And like I said, they can be because this is what I'll talk about on the next slide. So, but because I can get light to interact with that electronic degree of freedom, and then I can connect the electronic spin degree of freedom to the nuclear spin degree of freedom, I essentially have the ability to use light to connect a bunch of these things together. So I can have a very high density of them, and then I can connect them all together. And what I need is a way to basically use the photons that can interact with the system, and a bunch of beam splitters and switches, which I'll tell you about in the next couple of slides, to connect all these things together in a very special way. Okay, so this is essentially the way that we're going to use them. Okay, so this is the sort of the basic operation that we're going to be able to use to make our quantum network. Okay, so basically we have sort of a qubit over here. Okay, and this qubit, okay, is well, I shouldn't call this a qubit. It's actually two qubits. We'll call that the quantum memory, right? So this is a defect in our diamond, right? Silicon defect or a tin defect, okay? And this is another one, okay? If I shine, laser light on this tin defect over here, okay? As I said before, I can cause this thing to emit photons, okay? Now, they're not just emitting photons that go off into the world and have no connection to the atom that produced them. It is actually possible to do that, but it is also possible to have them emit a photon that is entangled with that electronic spin degree of freedom. So I shine my classical laser light, my little laser pointer here, on this silicon defect, and I can make it emit a photon. Okay, I also have to use some microwave pulses. I'll tell you there's more to it than just this, but if I use a microwave pulse, in addition to this this laser pulse, I can make it emit a photon that is entangled with the electronic spin degree of freedom. Okay, and one way to do that is such that you can actually make it be what's called, say, time bin entangled, meaning that the photon will be a superposition of two states, either arriving early or arriving late. And whether it arrives early or late will be, entangled with whether the spin is rotating on its axis so that the axis is like this, or so that the axis is inverted like that. Okay, so basically, it means that if the spin is rotating with, around like, say clockwise, if you're looking down on the electron, that's a very bad analogy, but we'll make it. If it's rotating clockwise looking down, it would arrive, say, early. And if it's rotating counterclockwise looking down on it, it would arrive late. Okay. And so if you, say, measure the photon as having arrived early, it will be spinning up. If you measure the photon as having arrived late, it will be spinning down. Okay. And you don't know what it's doing before you make the measurement of that photon, right? So, but when you measure it, no matter how far away you are, you instantaneously know that the electron is doing what I just said. Okay, so that's this property of entanglement, right? I have two possible states for each of these particles now, this photon and this electron and its spin. And if I were to measure the photon, I will instantaneously determine the state of the electron, even though it was in a superposition before. It was unknown, right? Essentially it was in both states before. I make the measurement, it's instantaneously in just one of those states for the spin. I mean, I could also do it the other way. If I had an independent way of measuring the spin, I could instantaneously determine whether the photon would arrive early or late, right? Now, I can't use that to communicate, right? I can't transmit ones or zeros deterministically, right? Because I don't know what the spin is doing to start. When I send this entangled photon off, I don't know if the spin is up or if it's down. If I make a measurement on the spin, it will either be spinning up or spinning down, and that will determine whether the photon is arriving early or late. But I didn't have any ability to choose whether it would arrive early or arrive late, right? So that's the whole thing about not being able to communicate faster than light, even though the reaction to your measurement does actually propagate faster than light, right? This has been shown. People have done experiments where, they'll do this kind of thing where the two particles are what's called space-like separated, meaning that I can make a measurement, say, on the photon, and then quickly make a measurement on the spin. And when I make the measurement on the photon, the time it would take light to travel between where I make that measurement on the photon and the electron is longer than it takes me to make the measurement on the spin and then read out the answer. And you can show that, in fact, yes, like the correlation, like, I'll keep doing this experiment over and over and over again. And I'm measuring, like photon arrives early, photon arrives early, photon arrives late, photon arrives early, photon arrives late, early, late, right? And I'll build up this huge set of data of early and late. On the other end, I was simultaneously measuring spin up, spin down, right? I'm not saying them correctly, but they always, have these anti-correlated pairs, right? And then when I compare the record at the end, I've got, Charlie sitting over here making the measurement on the photons, and Alice over here making the measurements on the spin. When they compare their results, they will see that, yes, in fact, they were always perfectly anti-correlated, right? Whenever I measured up over here, I measured, whenever I measured early over here on the photon, I measured up on the spin. And whenever I measured late on the photon, I measured down on the spin. The time, okay, that it would take this, for you to use a signal to communicate between those two was longer than the time it took to make, the two measurements and right. So what that means is that there's no possible way that there could be communication between these two things, like actual communication that was influencing the result, right? You can't say that, oh, there's some hidden variable we don't know about that communicates information between them, and that's what you're really measuring. It's not actually that they're entangled. It's just that when you're doing this thing over here, it's somehow emitting some energy that's traveling at the speed of light and influencing what's happening over here. No, you've ruled that out because you've separated them by a distance that is longer than the time it takes to make the two measurements. And so, you know, when you compare your record at the end, you see, oh, wow, they were really correlated in this very specific way that we call entanglement. And there was no possible, you know, even luminal signal that could have propagated between them to influence the result. They were just entangled, and the properties were determined when I made the measurement on one. They were determined at the other one at a speed that traveled faster than light, right? So that's called space-like separation, and there have been lots of experiments showing that entanglement is valid over, you know, space-like separations. And in fact, even at like stellar levels, there was a Nobel Prize given a couple of years back for showing that that entanglement could, you know, that you basically have like things separated by kind of you know, enormous distances. I think like across like two mountains, basically, they have this observatory on one peak and observatory on a different peak. And so they had this huge separation, and they were using starlight to measure entanglement and show that, you know, with this like very, very large separation that they had these entangled photons. There was no way that there could be communication between the two measurement spots, but nevertheless, they were entangled. So anyway, so I would encourage you to read that stuff. But back to our task at hand here. So I am going to stimulate this, you know, this thing with my magnetic pulse and my laser pulse to emit this photon that is entangled with this spin. At the same time, I'm going to stimulate this photon to emit this photon that's entangled with this spin. Okay. Now, when they arrive here, we've got this thing called an entanglement swap circuit. Okay. Now, what the entanglement swap circuit actually is a beam splitter and a couple of detectors. Okay. So what you can imagine is that these photons are going to interfere on a beam splitter. I will draw. So there's actually oops, cannot draw. I will use my pen pointer. Okay. Oops, I will try to use my pen pointer. There we go. Okay. So what you can imagine that there's essentially a mirror here. Okay. But didn't do a great job drawing a straight line. There's a mirror there. It's very straight. Very straight. It's the straightest line you've ever seen. And this mirror is 50% reflective coming in from either direction. So this photon is going to come in, and half of it is going to transmit this way, and half of it is going to reflect that way. And this one is perfectly aligned, no wavy lines at all, so that it will hit this beam splitter, and half of it will transmit along top, on top of the other one's reflection, and its reflection will perfectly align and travel along the top of the other one's transmission. So now I have these two paths coming out where I can't tell which photon is contributing to the signal, right? So the path information about which photon has produced the signal in each of these two output channels has been erased. That path erasure function produces additional entanglement now between those two photons, and consequently these two spins. Okay. Now, if I have a detector over here that can measure the number of photons that come out in each channel, the measurement of these photons will obviously destroy the entanglement of the photons, but you can show, and it's a bit complicated for this level of a class, so we won't do it, but you can show that what happens is there's a specific set of click patterns that we will do what we called herald the entanglement of these. So I stimulated entangled photons to be emitted out of both. They were initially only entangled with their emitter, with their quantum memory. Okay. when they interfere on this beam splitter, they become entangled with each other, and the whole system becomes entangled. When I measure out the entanglement of the photons in these two detectors, then what I end up with is when I get a specific click pattern here, meaning I measure, say a photon here, or a photon here, or two photons here and none there, et cetera. There's a specific set of click patterns that herald the entanglement of now these two spins. So what I've done is, through this entangled photon emission process, I've now entangled an electron spin there and an electron spin there, okay? So that is called a heralded entanglement swap. It is kind of the fundamental operation that you need to do to create a quantum repeater, okay? Now these electrons can store that entanglement for a little while, okay? What's a little while? Like maybe milliseconds when they're cold, okay? Cold meaning, for the tin vacancy, maybe 1 degree above absolute zero or less. For the silicon vacancy, might have to be, maybe if yeah, some caveats here, but like it could be as hot as 0.1 degrees above absolute zero, but more than likely you're going to want that silicon vacancy to be something like 0.01 degrees above absolute zero. And talk a little bit about more why later, but they have to be very cold. So the electron can retain that entanglement now between these two things, between these two electrons for a little while, for not quite for a second. Now, however, if I apply my microwave drives and I transfer this quantum information into the nuclear spin qubits, okay, so I'm just going to essentially swap it, into the nuclear spin here. So I would normally pick another color, but I won't waste your time with me trying to find the other color here. So that I'll swap it into the nuclear spin qubit there, maybe swap it into the nuclear spin qubit here. Okay, then I can hold on to this entanglement between these two nuclear spins, which will be entangled with each other for many seconds. Okay, which is a long time. For these kinds of processes, right? The time it takes to make the photons, emit these entangled, the time it takes to make these vacancy centers emit the entangled photons is more like, tens of nanoseconds, say. And so I can do a lot of these in the time, that the nuclear spins will stay entangled with each other, right? For many seconds, I could do, potentially billions of repeated operations like this. Now, why do I want to make repeated operations like that? Well, I'll show you. Okay, so this is a paper from the Center for Quantum Networks Deputy Director Dirk England's group at MIT from, I guess about 5 years ago now. So Chuck Choi was the first author here. That's the citation at the bottom. And the other co-director in the center, Saikat Guha, was also a co-author on this paper. And what this paper describes, and this is going to get a little bit heady, okay, but I want to try to explain it in a way that helps you all follow along, okay? What this paper describes is that a way to make what's called a cluster state, okay? Now I will come back in a minute or so and explain to you what a cluster state is and why it's useful, okay? But let's start with the ansatz that we want it, okay? So we would like to create a cluster state, okay? Now, what is a cluster state? A cluster state is a quantum state of technically two or more, but in this case, what we're really going to be interested in is many of these nuclear spin qubits, okay? We want many of these nuclear spin qubits to be entangled with each other at the same time, and not just pairwise entangled, but sort of on a two-dimensional map like this. So what does this mean? So this is sort of an abstract depiction of a bunch of nuclear spin qubits, say, and what it means is that this qubit is connected to this one, entangled with that one, and this qubit is entangled with this one, and this one is entangled with this one and this one, right? So everywhere there's a red line here, those qubits are connected together. And what we are trying to do is build up the degree of entanglement here to a very large degree. And we have to do that faster than they decay, right? We're trying to build up this entanglement across these many qubits together faster than that entanglement is decaying away. And if we can do that, if we can get to a threshold where the probability of entangling neighboring qubits is, say, above 50%, and you can do that faster than the rate at which they decohere, then you can show that you will asymptotically converge on a state that is such that almost everything in this lattice will be entangled, okay? If they're all connected photonically. Okay, so this is a cluster state, right? It's this like sort of massive entangled state with a very large degree of connectivity in terms of things being entangled with their neighbors, their nearest neighbors. And if they're entangled with their nearest neighbors, and then their nearest neighbors entangled, you know, in some connected graph all the way down somewhere else, then everything is basically entangled together. So these massive entangled states, these massive cluster states, they occur in this picture by a process called percolation, meaning, you know, it's sort of like percolating up from individual, you know, entanglement operations. So what's going on with each of these, you know, these little nodes here, these nuclear spin nodes, is that they are part of this system we just drew, right? So I have my electron spins and my nuclear spins, okay? And I have beam splitters and detectors. And this is like one little node. Well, actually, this box here, well, let's see. Okay, let me back up. I guess I cannot erase that. Okay, this is like one diamond vacancy center. Okay, it's got an electron spin qubit, and a nuclear spin qubit. And this is another one. Okay. And in the physical layout of this system, they're going to be here in these little red bars. So what these red bars are, you know, little chunks of diamond, basically, that have, each one has, you know, one of those vacancy centers, at least one, right? So it's got, there's a vacancy center here in that red bar, and a vacancy center here in this red bar. Okay. Now, there's a beam splitter, okay, over here. This is actually a beam splitter called a directional coupler that Shelby is going to tell you about when I shut up. And these are single photon detectors. So even though this system looks a little bit different, it is exactly what we just drew. Okay, it is, there's a beam splitter that connects two optical channels between the two electron spins and two detectors. And there's also, you know, each one obviously has its nuclear spin qubit. Now, these big blocks here are just switches. What do these switches do? Well, they allow you to connect between any of these four outputs, right? So there's an output here, there's an output here, there's an output here, and there's an output here, and there's one input, okay, which is from the color center. And if I look over here, same thing. There's the input from the color center, there's an output here, 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 and here. And this is a switch. This means that I can choose where the output is going to go. So in this case, I'm going to choose the output to go here, and I'm going to choose this one's output to go here. Those photons are going to travel to this beam splitter. It doesn't look like the little box beam splitter I drew, but it works exactly the same. I have two inputs, two outputs. They're gonna split. So this one, 50% of its energy will go this way, and 50% will transfer into the other arm. And this one, same thing. 50% will go this way, overlapped with the other one, and 50% will transfer to the other arm, overlapping with its kind of straight through transmission. So this thing is doing the same thing as a beam splitter. Okay, it is a beam splitter. Okay, we call it a directional coupler, but it's a beam splitter. And now these photons, which have now been entangled with each other, just like before, will go to these single photon detectors, and the click pattern will determine whether or not these have successfully been entangled with each other. Okay, it's not deterministic, it's probabilistic, but when I get that specific click pattern, I will herald that these have now become entangled with each other. When they have, okay, when I entangle these two things together, what I'm going to do, I'm going to do what's called shelving the entanglement of this one in its nuclear spin. So I'm going to transfer that to the nuclear spin. Okay, that's going to free up its electron to now do the same thing again, but I'm going to try to do it, say, with the color center over here. So now I'm going to reconfigure this one switch to come down here. And I'm going to reconfigure this one switch to go up here. And now I'm going to try to entangle this color center, its spin qubit, electron spin, with this electron spin. And if I successfully do that, there's a way to actually entangle the three of them together by manipulating the nuclear spins with a magnetic field and then stimulating them to emit photons again. So again, like it gets a little bit complex at that point, but there's an operation I can do to now entangle the three nuclear spins together. Okay. And if I do that successfully, well, now I'm gonna start trying to entangle this one with this one, and this one with this one, or that one down there. And that's how I'm gonna build up this cluster state. And I'm not just doing it right here, starting with this little seed. I'm going to start, say with like many seeds, and I'm going to be trying to build up, a little small cluster over here and a small cluster over here and over here and over here, right? I'm going to be trying all over the place within this thing to build up these little small clusters. And then eventually, if I can do it fast enough and with a high enough probability, they will all connect together and I'll get this percolated cluster state, this very large entangled state. Now, the reason why we want to do that is that with that cluster state, again, way outside the scope of a class like this, but you can show that you can, just by making measurements now on these nuclear spins, which you can do by transferring that nuclear spin state into the electron and then measuring the electron state by causing it to emit photons, okay, and then detecting those individual photons, not entangling anything anymore, just literally, I want to measure this one spin state now, okay? So I transfer the quantum information to the electron spin, I cause it to emit an entangled photon that just goes into the detector, and I make that measurement, and then now I've measured the state of this electron spin. If you can do that, okay, make those measurements now on this large entangled state, you can actually drive quantum gate operations, quantum computations, essentially. And in the context of quantum networking, it's a little bit weird, but the actual operation that we want to drive, the quantum computation that we want to drive, is what we call entanglement distillation. And if you took Professor Guha's course earlier this week, I'm sure he would have talked about entanglement distillation. But essentially, entanglement distillation is the following. So we've been talking about this entanglement as though it's perfect. It's not, okay? It's not perfect because these detectors have some noise, right? They sometimes just produce clicks on their own. Not often, but every once in a while, they'll produce a click even when there wasn't a photon present, okay? Similarly, all these lasers that I'm shining down to produce these emitted photons that come out entangled, sometimes those photons will just accidentally scatter into the waveguide, and there's a huge number of photons that I'm using to make these guys all stimulate these emitted entangled photons, and only one photon comes out, right? So maybe I'm putting in 10 to the 15 photons or something, probably not that much, but maybe I'm putting in, say, like 1 billion photons into this system to make it emit one. Well, if any of those other billion photons make it into a detector, well, they make it click, right? It's a single photon detector. It will click. Now it clicks with nothing to do with the quantum operation that I was trying to do. It essentially clicks from noise, right? It's unwanted. So whenever those unwanted clicks happen, and I can't tell them apart from the good clicks, those occasionally cause me to think that I have heralded entanglement between two things that really weren't entangled. It was just accidental, right? And similarly, sometimes the photons get lost. So sometimes I do quantum operations. You know, I try to produce entanglement, but the entanglement doesn't work. So that actually just reduces the probability that it all works. But in addition to that, there's this noise that I just talked about, and the noise makes it so that the here, I'll back up a step. So if I only had loss, that would be okay, because I'm heralding the entanglement. If there were no noise in the system, so that whenever I had this particular click pattern, that would actually herald perfect entanglement. Now, it reduces the probability that it's going to happen if those photons can get lost, okay? But it would still be perfect whenever I do make the click pattern. But the noise makes the click pattern essentially false sometimes, right? It's a false positive. And those false positives mean that you think something is entangled that really isn't. And that is called entanglement infidelity, okay? And you can imagine that if I'm trying to use this to connect two things quantum mechanically together, and I think that they're entangled and they're not, well, like I was saying before, maybe it's two quantum computers that are connected together. This one's doing something very particular, this one's doing something particular, and they're counting on being able to make measurements over here that instantaneously affect and change the states over here. Well, if you're doing that and it's not actually changing the states because they're not entangled, that's an error in your quantum computer. And it means that you're not going to get the right answer in your quantum computation. Okay, so these entanglement errors, these entanglement infidelities that are produced by noise in the system mean that I will have some error in whatever I'm trying to do with the quantum systems that are being connected. Okay, so the specific in the Center for Quantum Networks, the specific quantum operation that we're interested in here is what's called entanglement distillation, and it's a little bit complicated, but basically what you can do is the following. You can sort of think of what I'm doing here is creating a bunch of redundant copies of entanglement, okay, in this big cluster state. And then by going and making measurements on things and reducing it to, so when I make the measurements, I actually get to read out the state. And I can see basically if things are entangled or not, right? And I can make a measurement on a bunch of these qubits out in the field here to I'll reduce the size of the cluster state, right? So I'm destroying entanglement all over the cluster, and it's going to make it a smaller cluster, but that smaller cluster can be entangled with a higher fidelity. Okay, and then I can take a large degree of low fidelity entanglement and produce a much smaller number of qubits that are entangled with a much higher fidelity. And that's what I need. Okay, I want high fidelity entanglement to do reliable, essentially quantum entanglement of things across my network. Okay, so that is really the core of what we're trying to do in the Center for Quantum Networks. Okay, now I'm almost done with my little bit here, and then I'm going to take a break, and Shelby's going to completely change topics. It'll be a lot more. It'll be a lot easier. Yeah. But what I want to say is, let's think about what we actually need to do this, right? I mean, we've laid out this like protocol, this architecture for being able to create massive degrees of entanglement and make measurements to create a very high purity of entanglement. But what do we need to actually do this, right? Well, we're going to need a very large number of qubits, okay, in little chunks of diamond, connected together with photonic channels that guide the light, right? So when this thing emits an entangled photon, it can't just like go off into free space somewhere, right? It can't like shoot off over there, right? And this one, like shoots off over there. No, this thing has to travel along this channel, okay, and go through this switch that can exactly determine which way it comes out. And then it has to exactly divide in half with the photons coming from this channel that were coming out of that switch and that diamond chunk, right? So what do we need here, right? We need a way to put diamond chunks into, in a very large number of them, a very large number of diamond chunks into a very large number of what we call waveguides, photonic waveguides, connect them together with a large number of photonic switches, and then connect those together with beam splitters or directional couplers, Okay, again, large numbers of these things. And we need those to all terminate in single photon detectors, a very large number of single photon detectors. Those are kind of the core elements we need. There are more things than that we'll talk about as we go on today, but those are really kind of the core elements. One of the big things here is that, you know, if we're gonna make a whole bunch of these things on a chip, we really want as many of them as possible to actually work. So we want to be able to make a huge number of them, and we want to make sure that they all work. So what we're going to talk about primarily for the rest of the class, okay, is how we're going to make a large number of these things. Well, how we're going to make them at all, right? How we're going to make a large number of them, and how we're going to ensure that they mostly all work, okay? And that is really the what the kind of core technical content is going to be, but what we're trying to achieve is this, okay? And that's why I wanted to spend, you know, whatever, an hour apparently on this introduction here, okay? With that, I am gonna hand it over to Shelby. We can take a 5-minute break. Maybe people can recover their blood sugar. This is actually the last slide, okay? What I'm showing here is a pretty famous photonic quantum computer that was built in China by the group of Zhangwei Pan. In about 4 years ago, they were able to show that they could do a quantum computation using light that was physically impossible with modern supercomputers, okay? But look at this thing. That is complicated, right? So this is each one of these little things here is a different mirror. There, you know, mirrors over there. There's all these fiber cables coming everywhere. Like this is a huge room full of stuff to be able to make this quantum computer, okay? And what it's doing is it's using about 100 photons at a time to do a quantum computation. Now, this is much like sort of, you know, agrarian farming, right? You know, it's like very manual, right? A person had to physically bolt each one of these components onto a table, align it so accurately it would boggle your mind, keep it aligned over time, right? And it's really just, it's not scalable, it turns out. Like as we make these things larger and larger, doing all this and keeping it aligned becomes, you know, exponentially harder, at least polynomially harder, but a polynomial scaling that we would all not like, okay? Now, on the other side, this is a pencil eraser, and this is a chip from Intel that has a transceiver that takes 25 40 gigabit per second modulators, okay? So it's sort of a complicated optoelectronic device that can modulate the amplitude of light. And this chip is essentially the state of the art in data center communications, and it's the size of a pencil eraser. And it contains more photonic components and really more complexity than this whole room full of stuff, okay? And this is sort of the equivalent of like modern industrial farming, right? So like if you imagine these people trying to farm this much land compared to this like array of, you know, I would guess in this case, sort of like, you know, roboticized, not man-powered driven combines, right? Look at the amount that they can do in the same amount of time that they can do, right? That you can do thousands of acres in the time that it would take, you know, the same number of people to do, you know, a few acres, right? And so we're trying to figure out how to scale up these kinds of technologies using mirrors and beam splitters and lasers and stuff in free space into stuff on chips that is made, you know, with billions of little components at a time. And that's really what we're going to be focused on. And we need to figure out some way of doing that. We're going to tell you about that, how we do that today. Okay, and so with that, we're going to take that little 5-minute break, and Shelby is going to tell you about photonics, and which is really the key to doing all this stuff at scale.
10:10.
Yeah, 10:10 we will, well, at 10:10 Mountain, we will return, and Shelby will tell you about photonics.
Yeah, hopefully people can give me help, and I apologize because we didn't have a separate chat for the Q&A, so now I'm aware of that one again. And I guess if people can't hear me, they won't know what to say anything right now, but that's fine. Okay, so we're gonna move on. This is.
Hey, Shelby, it's a little hard to hear you. Can you? I think we're running off of Matt's computer, so if you could move just a little closer to his or talk louder.
Switch seats if you want, or I can.
Can you go to your microphone settings? And see which one you're. Yeah. Okay, can you go to the conference one?
Sure.
Yeah.
Okay, Brianna, is this better? Can you hear now?
Yeah, much better.
I guess we can. Did you just mute your microphone?
I did, yeah.
Okay, Brianna, can you hear us?
Yep, good,
Okay.
and no feedback.
Okay, all right, perfect. Okay, yeah, so now switching gears, we're gonna, very high level, super high level, just so that everybody has all the right terminology and everybody's on the same page. We're gonna quickly go through this sort of what is photonics. So the actual definition is a branch of optics that involves generation, manipulation, and detection of light. The generation would be lasers. Manipulation is things like waveguides, modulators, and then detection is detectors. We'll mostly be talking about the manipulation part of it today. But obviously there's a lot of different applications for photonics, ranging from information processing, photovoltaics, which is where people are collecting light energy, converting it into electrical energy, spectroscopy and holography, and then finally telecommunications, which I think we are lumping in quantum networks into that. So first thing we'll talk about is just some waveguide basics. So Snell's law is an optics law. It says that if you have an interface, if you have light interacting with an interface of two different materials, then the refracted angles will follow this Snell's law, where the index of refraction on one side times the incoming angle sine theta will then equal the index of refraction to the outside times sine with that this angle theta 2. So looking at this, we can do some math here. We can say that if we want all of the refracted light to be 90 degrees, we can find this critical angle, which is just sine theta critical over N2 over N1. So we can translate that into this waveguide structure. This is the most basic waveguide structure we'll look at. It's a planar slab waveguide where you have a high index of refraction N1 separated by 2, or the same lower index of refraction N2 and N3. So using Snell's law, we can say that if we have an incoming beam at this this angle related to the critical angle, then we can get total internal reflection throughout this waveguide, which means that all of the light is going to be reflected off of this surface and none of it will be refracted out of the waveguide. So we can essentially propagate this light along the waveguide in whatever configuration we would like. So we're not going to go through E&M theory today. I'm just going to tell you some things and you should trust me a little bit. But here we have depicted, it's essentially what our index of refraction looks like. It's a rect function where we go from a lower index to a higher index waveguide. You can use Maxwell's equations, run through all of the boundary conditions for this, and you can get a couple parameters. The first one is the phase constant. And this is basically telling us how the phase propagates throughout our waveguide. And then we have the K vector, and the K vector is what describes that actual propagation. Before, when we were looking at it, we have these kind of, the light is bouncing around the waveguide at this total internal reflection, or a series of total internal reflections. What we do when we go through this, Maxwell's equations math that we're not actually going to go through, is we can get this effective index. And the effective index is basically saying if we have this geometrical structure with these different refractive indices, the effective index is essentially going to be in between our different refractive indices. So if we're going from 1 to 2, the effective index will be somewhere between 1 and 2, depending on your geometrical structure. And that effective index is going to, you're going to have a certain refractive index for each of these modes that will propagate in your waveguide. So we have on the right here, these are depictions of different modes within the same waveguide. The top one is the like the mode structure, what it looks like, and the bottom is the intensity. So it's just the top one squared. So as you can see, you have multiple different modes that can propagate within this kind of geometrical structure. And not all of the mode is fully confined to that core, to the core of our waveguide. So some of it is in what we call the cladding material. That's the lower index of refraction materials. This is all just to say that you can have multiple modes in a waveguide depending on if the geometrical structure allows for that. That's depicted in what's called here, it's called a BV diagram, and these parameters B and V are derived through our Maxwell's equations, waveguide theory math that we skipped over. But this is all just to say that depending on your indices of refraction and the geometrical structure of your waveguides, you can have multiple modes propagating in it, or you can reduce it down to single mode depending on what you want to do. Yeah. So moving on, there's a couple of different waveguide configurations. The simplest one is a strip waveguide, where you, or rib or ridge waveguide, I guess, depending, where you just have your higher index, which is this N2 right here, sitting on top of your lower index material. And then we have embedded strip waveguides, where it's almost fully surrounded by the lower index material. And then we have strip loaded waveguides, where you have a layered structure of refractive indices. So these different geometries, the different and the different indices of refraction of your materials are going to change both the number of modes you can have and the confinement factor. So how much of that of the mode is actually confined to the core of your waveguide rather than in the cladding of your waveguide. But these are just to show you a couple of different options that you have for fabricating waveguides. Next, we're going to talk about loss mechanisms in a waveguide. Obviously, we want to reduce loss as much as possible. So there are a couple of ways that we're getting that. The first one is coupling loss, which is just if you're going from a fiber to a chip, or if you're going from different devices on your chip, you'll have some degree of coupling loss that you want to account for and try and minimize as you're doing your designs and fabrications. The next one is absorption. Most materials are going to absorb light at least to some degree. So the longer path lengths you have on your chips, the more absorption you'll have. And then there's things like radiation loss, which comes from bends. So as the light is propagating through a bend in your waveguide, you can get some loss through this evanescent field, which is, I think of it as like that tail of the mode that isn't fully confined to your waveguide. And then there's scattering. There's two types of scattering. The first one is Rayleigh scattering, which is when it's interacting with something that's much smaller than your wavelength. So this is things like small surface roughness and whatnot. And then there's Mie scattering, or MIE scattering, which typically comes from larger defects. If you have essentially, bigger defects other than just small surface roughness and things like that. Next, we'll go on to very quickly go through some important photonic devices that I think we'll talk about. The first one is a simple Y splitter. So we have at the bottom here, we have our regular waveguide. And then as the light propagates through that, it ends up getting split into these two different arms. So that's a way to effectively move your power across your chip, redirect it to different places. And the next one is what Matt talked about earlier, is directional couplers. So I mentioned very briefly the evanescent field. One cool thing about an evanescent field of a mode is if you bring these two waveguides, if you bring them very close together, eventually, if they interact long enough, they can evanescently couple to something that's very close to it. So what happens here is you see as you propagate along this directional coupler, you start with all of your light in the top waveguide, but then eventually as it propagates, it ends up fully into the bottom waveguide. And if you continue that, it will just move back and forth. So what Matt was talking about earlier with beam splitters is where instead of making it long like this, if you were to make it, looks like 1/8 of this length, then you would end up with only 50% of your initial mode moved into the bottom waveguide. So that effectively works as a 50-50 beam splitter that Matt was discussing earlier. Another important device is a Mach-Zehnder interferometer. So this starts with a Y splitter and then a Y combiner. The way that this works is because you have an incoming field that has a certain phase to it. And then if you break it off into two different arms, if the length of those arms is different, then you can change how they are constructively or destructively interfering at the end. So you can do this in a passive manner where you purposely make one of the arms longer than the other one so that the optical path length changes the phase of one arm so that when they interact at the end, you can either fully interfere them or constructively or destructively. I was like, what is that word? Okay. Or destructively interfere them. The other option is to, so that would be an example of a passive Mach-Zehnder interferometer where you have a sort of set interference pattern that you want to use. The other option is to make an active Mach-Zehnder where you have an electro-optic material on one arm. There are some materials that respond to electric fields where it changes the index of refraction so that you can change the optical path length to your desired interference pattern. So this is an example of things that people use for a really common one is modulators. So you can modulate between fully constructive and fully destructive. So you can have that binary 1-0 pattern when you're doing telecommunications. And the next one that I think is important is resonators. So a resonator is shown at the top right where you have a bus waveguide incoming, and then you can evanescently couple to this ring waveguide structure. So this is set up so you can imagine that as the light is propagating along the ring, for certain wavelengths, they can create a standing mode, which means that once it loops back around, it overlaps perfectly with itself, constructively interferes, and the wavelengths that can do this within a resonator structure are what we call resonant wavelengths. And so these are usually characterized by their Q factor or their quality factor. This equation here is describing that. So it's based on the radius of your structure, the effective index, the resonant wavelength that you're looking at, and this kappa squared factor, which is a coupling constant. So it's how well or badly you are coupling into your resonator. And then we have the free spectral range, because the way standing modes works is that if you have one wavelength that can resonate as a standing mode, then you'll have other multiple wavelengths that will also resonate within that structure. So we can do this, you can either have it as just a single bus waveguide where you have an incoming where you have this incoming waveguide and no other ones, or you can pick it off on the other side and direct it somewhere else. So that's an example of using it as a filter to pick off certain wavelengths. And then the other useful thing about resonators is that they're tunable. You can tune them either electro-optically, like we talked about with the Mach-Zehnder, where we change the effective index and therefore the resonant wavelength, or you can tune them thermally or magneto-optically, and probably other ways also. But so these are kind of our important devices that will come up today, most likely. And then now we want to go on to talk about important optical effects. The first one is the Purcell effect. So this is a way to enhance the spontaneous emission rate of quantum systems by altering its environment. So what we discuss here is taking that the atom You know, for instance, in the vacancy centers that Matt was talking about earlier, and putting them in a resonance structure. So what this does is, if we send in our light to excite our atoms, and then they, you know, then drop down and release the specific photons, what this resonance structure does is it allows light to continually pass back and forth, so you can get more interactions with your atoms and a increase in the spontaneous emission rate. So I forget what F stands for.
That's.
Frequency? Yeah,
That's the Purcell, that's the Purcell.
Oh, that's the Purcell.
yeah. So as you can see here, so it's proportional to, this is the wavelength in vacuum, the index of refraction of your resonant, like the environment in your resonance chamber, and then the Q factor of your resonator and what's called mode volume. So we can see here that if you want to increase the enhancement of your spontaneous emission rate, you can either increase the Q factor or you can decrease the volume. So the smaller you make your resonance structure, the more interactions, or the more quickly you get interactions with your atoms, so you can increase this emission rate. And then finally, we'll talk about some nonlinear effects. So nonlinear optical effects occur in medias where the polarization density responds to an applied electric field non-linearly. So we have this equation here. The first term is just our linear response. When we talk about regular optics, this is usually the only term that we're looking at. But if you're working with higher power fields, you can get second or third order effects. So this second order nonlinearity is where we say 3 waves mixing. And then for third order nonlinearities, we'll have 4 waves mixing. And this looks like we have 3 ones here. The first one is spontaneous parametric down conversion, which is a second order process where you have an incoming pump signal, and then you get an output signal and idler frequency, where the signal and idler frequencies are the summation of those are equal to the pump frequency. And then there's some frequency generation, which is also second order, where you have 2 incoming photons that then add to the frequency of your output photon. And then 4-wave mixing. So 4-wave mixing is a third order effect. So you have 4 beams interacting, where you can have some combination of 2 to 3 incoming waves or incoming frequencies that then combine to 1 or 2 output frequencies. Spontaneous SPDC and 4-wave mixing are used in entanglement generation of photons, and some frequency generation is useful when you're converting between different wave bands, because different photonic devices will work better at some wave bands than others. So just when we're talking about fabricating devices, when we're talking about active versus passive, passive is where everything is, it's made to not, essentially there's no electro-optics in there. So everything is built to do one thing, whereas with active devices, you can have variability, or you can change the function. So for passive devices, they're usually much simpler to design. There's fewer fabrication steps, and they tend to be a bit cheaper. But with active devices, you can have a lot more versatility and functionality in your devices, and you can have reconfigurable systems on your devices, but they are more difficult to design and fabricate. So there's trade-offs depending on what you want to do, on which ones you actually want to use in your setup. Just really quickly, some common fabrication materials: silicon, silicon dioxide, and silicon nitride are typically used a lot in waveguide structure, especially in passive optics. Lithium niobate, gallium arsenide, and aluminum gallium arsenide they have some strong nonlinear effects. Particularly lithium niobate, which has strong second order effects, which are typically easier to work with because they don't require as much power. And then you have things like chalcogenides, which do have high nonlinearity, but they typically work better at longer wavelengths. And then you have polymer devices, which are really versatile. they're easy to work with, but they don't often have a lot of structural integrity. But they can be used really freely, and they can be altered really simply. So sometimes there's a place for those as well. And then the last thing, we'll just go through a really quick fabrication process. So when you're designing something like this, you'll start with a substrate with whatever you want your waveguide material to be. In this case, we're looking at silicon. So the first thing you'll do is you'll deposit a resist, either a photoresist or an e-beam resist. There's two types of lithography that I know of, photolithography and e-beam lithography, where when you expose them to either the e-beam or this light, usually UV light, then this photoresist is going to react to that, either positively or negatively. One of them, when you expose it and then develop it, the part that you expose remains there, and then for the other one, the part that you don't expose is what remains. But so you end up with this pattern structure that you want on top of your waveguide material. And then you can etch through your waveguide material without fully moving through your resist. We call this masking. And then you can finally wash away your resist and then apply a cladding layer. You can also repeat these steps to have layered materials or devices. There are multiple ways to mask, multiple ways to expose. And maybe Matt is going to talk about that. I don't know how much you're going into foundry work, but this is the very basic process for a very simple waveguide. And that's it. That's a very quick overview of all the things you need to know. And did you want to talk about foundry still?
Yeah.
Okay, cool.
I guess I was planning on talking more about fabrication, so if you want to spend any more time talking about the actual details of fabrication.
Well, I mean, I can, but it's, it's pretty device dependent. I figure it's a whole class on its own.
Yeah.
Yeah.
What do people see on Zoom now? Okay. So, I'm gonna talk a little bit about the kinds of manufacturing processes that we want to use here. Actually, I want to try something. I don't know if this is going to work, so I want to see if I can play a video and you all can hear it. If you cannot, then we will abandon that. But give me 1 second. What's showing up on Zoom right now? Nothing, just us.
Just us, I think. Yeah.
Okay.
Oh,
I
wait.
need to see if I can find this.
Oh, no, that's showing.
That's showing. Oh, that's not what I want to show, but okay, I'll give me a minute. Okay, we're gonna try this. Share this one. Nobody sees that yet. I guess I have to move it over again.
No, we
see
can
it
see.
on-
Oh, okay, you could see it before. Okay. So let's do slideshow. And then I'm gonna play this, and I guess my concern is that the audio will not come through. So I'll just ask people to say in the chat quickly when it starts if they can hear the audio for this video or not. Oh, okay, this assumes that I can actually start the video. This. This is not working, is it? Okay, give me 1 second. I'm gonna just see if I can find the YouTube video. Share this. This is making me feel real old, so I apologize. I guess, okay, here we go. You guys see? anything?
Yes.
Is it a video? Yeah, okay. Okay, now the real test will be whether everybody online can hear the audio, so please tell me if you can, I'll make it full screen.
Yeah, you'll have to answer in the Q&A.
TSMC pioneered the dedicated semiconductor foundry business model with leading-edge technology, unmatched manufacturing capabilities, and customer partnerships. TSMC has established a competitive advantage to unleash innovations in the global semiconductor industry. TSMC continues to invest in R&D to provide the industry's most advanced and comprehensive manufacturing process technologies.
So I'm gonna pause it for a second. And I wanna just tell you why I'm showing you this video. Okay, so I want you to think about some kind of object, right? Like, doesn't really matter what. But what I want you to think of is what is the single thing you could think of that humans have manufactured the most of, right? Is it, cars? Is it ball bearings? Is it McDonald's hamburgers? Is it wheels? What? Like what thing can you think of that humans have manufactured the most of? We've made a lot of cars in the world. Let's think about, complex things as well. Maybe not super simple objects, right? But what have humans made the most of, right? How many cars do you think have ever been manufactured? I mean, if it were more than 10 billion, I'd be pretty surprised, right? And a car is a pretty complex device, right? But they're for most of history, they've been assembled by hand. And even with robots assembling them, they're essentially assembled serially, right? I have to put them all together, sort of parts one at a time. And I can maybe make a bunch of robotic assemblies, assemble them, in parallel to try to speed it up. But they're essentially, they're sort of manually manufactured, right? They're, whether it's robot hands or human hands, somebody's got to put these things together, connect them, right? There has to be like very precise, alignment of these big objects. Okay, now, and I'm sort of drawing a blank on maybe what, if you all want to answer in the chat of what you think might be another thing that humans have made like the most of, please chime in. But what? Paper? Okay, yeah, paper, right? So made lots of sheets of paper, but paper is pretty simple, right? It's a relatively simple device. It's important and all that, but let me even use paper as an example, right? I mean, I don't know, this would be like a Google interview question or something like, how many sheets of paper do you think the world's ever manufactured? But I mean, let's say it's 1 trillion, right? Or let's say it's 10 trillion, right? Okay. I mean, it might be more than that. I don't know. Maybe 10 trillion is an underestimate. Shelby's
I'm
Googling.
on it.
Yeah.
More than 40 million metric tons.
40 million metric tons. I don't know how many sheets of paper is that.
A lot.
Well, we gotta figure out how many sheets of paper it is. But anyway, it's gonna, it'll be some large number. But let me put this to you. Every chip in every one of your phones, in every one of your computers, every microchip, right? These electronic, microelectronic processors, they have billions of transistors. And each transistor is made up of, some large number of electronic circuit components. Okay, excuse me, I didn't mean to say that. Each transistor is individual, but the little circuits that they make up are made of individual transistors. But essentially billions of transistors. A transistor is a fairly complex device, right? And we put billions of them on every single chip. There are many billions of those chips in the world, and the number of transistors per chip is only growing, and the number of chips is only growing, right? Every car now, has a microelectronic processor in it, right? So when you think about the number of people and the amount of time it takes to make billions of something, right? It seems like it might be a lot, right? But that's actually not true. It probably takes of order maybe a day or two to make something like 25 wafers that are maybe 12-inch in diameter. Each one of those 12-inch wafers might have 1,000 little dies, and each one of those dies would have something like 1 billion transistors on them. Okay, so we're at 25 times 1,000 times 1 billion, so like 25 trillion transistors are manufactured in what we call like a little cassette. And a cassette is basically just like a little stack of wafers that move around together in one of these semiconductor foundries. And they can run many of these essentially at the same time, or at least one after the other. So the scale of manufacturing of microelectronics is beyond imaginable. I think like we can imagine it now because it's happening, but if you rewound back 50 years, nobody would be able to fathom the scale at which we manufacture transistors essentially. And we're going to talk for a little while in the rest of the class about trying to use some of the techniques and tools and material science that have been developed to make microelectronic circuits to make photonics. And so, but first I want to give you some impression of what it actually means to make these things at scale. And so, this video is from TSMC, the Taiwan Semiconductor Manufacturing Corporation, based in Taiwan, obviously. And TSMC is probably the most advanced semiconductor manufacturer in the world. They have these facilities that are essentially completely roboticized. So very few humans actually touch the wafers. The humans maintain the tools and they build the fabs and stuff, but the wafers essentially run on tracks, and everything is controlled by robotics and computer programs. So this is why I'm showing you this, because we are going to try to use these same kinds of techniques to make our photonic devices at scale, so we can have lots and lots of qubits, lots and lots of entanglement, and make scalable quantum networks. Okay, so now I'm going to show you the rest of the video, or at least some fraction of it.
The company manufactures over 10,000 different high-yield and high-quality customer-designed integrated circuits every year. These circuits are found in smartphones, high-performance computing, IoT, automotive electronics, and consumer electronics products. Let's look inside TSMC's fab and learn about the IC manufacturing process.
IC means integrated circuit.
A TSMC fab is primarily a large clean room. To maintain the cleanliness of the production environment, entry of the fab is strictly regulated. After passing through metal detectors and undergoing ID recognition, personnel wear clean room garments, gloves, face masks, and shoes. After changing into the appropriate attire, they enter the air wash room to remove all dust particles that could inadvertently be brought into the fab and which could impact production yield. At TSMC, the
I'm gonna pause it for 1 second. So when they say impact production yield, I mean, literally, you know, when they're making these 25 trillion transistors at a time and these 25 wafers, right? A very large percentage of them work. And you know, usually something like more than 99%, in fact, probably 99.9%. And the reason, one of the major reasons is because there is essentially no dust in these facilities. They're able to make these things in a way that is essentially contaminant free. Because every little dust particle is, you know, the size of probably, you know, thousands or maybe even millions of transistors. And so, you know, dust particles can completely take out a region of a wafer and make those things not work. And so when we talk about building photonics at scale for quantum computing and quantum networking, you know, we want to also be able to make these things in very, very large numbers. And so we're going to need to kind of leverage these same kinds of techniques. In fact, the same facilities, really.
manufacturing process is closely monitored and properly protected. Raw materials, such as liquids and gases, are delivered directly to various manufacturing equipment through a maze of pipelines to avoid external contamination. The clean room air conditioning system uses various filters to trap particles and maintain ultra-pure air quality. Temperature, humidity, static electricity, pressure, magnetic fields, and vibrations also need to be regulated. Integrated circuits, or ICs, consist of millions or hundreds of millions of transistors, electronic components, and metal wires that are shrunken down onto one single wafer. As ICs are getting smaller and smaller, their electronic signals are becoming more complex to accomplish an extraordinarily wide variety of functions. How can this seemingly smooth IC have so many components? Let's start at the beginning. To start, IC design engineers use a computer-aided design system to lay out the patterns for each IC's circuit diagram. They use electron beams or lasers to transfer the patterns onto a glass substrate called a photomask. A single photomask represents a layer of circuits. Some complex ICs require multiple photomask layers to complete a circuit's design. The more complex the IC, the more layers it has, and the more photomasks it requires. The raw materials for making integrated circuits are silicon wafers. The production of silicon wafers starts when raw polysilicon is heated and stretched into a cylindrical crystal rod. After grinding and cutting, the rod is thinly sliced into silicon wafers. Doping elements are added to change its conducting power and characteristics. The doped wafers are first fed into a diffusion area that produces high-temperature thin films to create insulation properties. These furnaces use precise temperature control and gas flow, along with a high-temperature reaction to bond silicon compounds onto the wafer's surface. During the chemical vapor deposition, chemical reactions convert gases into a solid state to form the thin film. Wafers are next sent to the photolithography area, where circuit patterns are laid out onto the wafer. The process starts with a thin layer of photosensitive liquid called photoresist, which is applied to the wafer's surface. A photomask is then placed on top of the wafer and illuminated to create a pattern on a partially exposed wafer. The wafer is then developed by washing off parts of the photoresist to reveal the pattern defined by the photomask. After photolithography, the wafer is sent to the etching area to remove those parts not covered by the photoresist. The remaining patterns are the designed electronic components. In the ion implementation area, charged ions are implanted into designated areas to achieve a specified concentration and depth that change the wafer's conduction characteristics and form the prototype of the final component. In order for the integrated circuit to achieve the functions given by the design, these electronic components must be connected with metal wiring. In the physical vapor deposition area, a metal film is sputtered onto the surface of the etched wafer. This metal film layer is then exposed to light, developed, and etched again. Materials are etched away to create the correct metal wiring. After each component and metal wiring layer is formed, the wafer is sent to the chemical mechanical polishing area, where mechanical and chemical reactions remove material on the wafer's surface to achieve planarization. This helps the subsequent thin film deposition to comprehensively planarize the wafer's surface for the next layer's process. The formation of each layer's structure needs to go through this process cycle, and layer-to-layer calibration must be very precise to allow electrical currents to flow smoothly. During the entire manufacturing process, wafers are stacked layer by layer and shuttled back and forth between different processing and manufacturing areas. TSMC took initiative by introducing an automated material handling system in their 12-inch wafer fab, along with an automated timely dispatch system that conducts machine dispatches, wafer handling, and machine processing. The fully automated system allows the entire fab to conduct smart manufacturing and machine learning. Recorded production data provides tracking and error correction to.
Yeah, I think I'll stop it there just for the sake of time. But let me share my screen again. Different screen.
Okay. To bring one, right?
That one. Yeah, okay. So, why did I show you this video of TSMC, right? Well, TSMC, and along with other companies that support TSMC have, and other companies like TSMC, Samsung, Toshiba, Intel, many others, IBM, right? These companies have developed these fabrication foundries that build these microelectronic circuits at a scale that is, like I said, sort of incomprehensible if you were to rewind yourself even maybe just sort of like 50 years and all of human history and all the ways and numbers of things that we've made. So, but it goes beyond that. They also have lots of simulation and design automation that allows them to sort of simulate the devices that they're making, so that they know what they're going to make through this complex process. With the photomasks that they design, they'll know exactly what device they're going to make, how it's going to perform. They have this massive infrastructure that you just saw a lot of about material science, automated manufacturing at these unprecedented scales. And then they also have testing and validation at scale, right? So they don't just make the wafers, they also test them robotically at large scale. And so all of these things are necessary to be able to make photonics at scale as well. What do we need to do? We need a good old-fashioned hijacking. Okay, we need to take our sort of diamond-centric photonic architecture, and we need to figure out how to hijack the manufacturing methods and material science and all the things we just talked about to make the photonic integrated circuits that we want. And we need to do that because we also need, millions or tens of millions of qubits on a chip, right? Just like you need tens of millions maybe or hundreds of millions of transistors, or maybe billions of transistors on a chip, right? We want to reach those scales as well. And so really the only practical way to do it is through that kind of manufacturing. And what I will tell you is that there are, lots of different manufacturing architectures for these kinds of electronic integrated circuits. You know, Shelby talked about some of these, but it's not just CMOS silicon that you can make in foundries. You can also make gallium arsenide based electronics in foundries, gallium nitride based power electronics in foundries, silicon carbide based electronics in foundries. There are different photonic materials that have, used some of the tooling and capabilities. Lithium niobate is a very popular material for the kinds of photonic integrated circuits that we make. If you listen to Marco Longcar's lecture earlier this week, you would have heard a lot about lithium niobate, but none of these other materials can rival what can be done in silicon CMOS foundries, okay? And so we want to take advantage of those silicon CMOS foundries that make these incredibly complex microelectronic circuits, and now make, what are called silicon photonic devices, which use the same exact processes and tools and methods to make devices that have photonics and electronics integrated with each other. We want to somehow figure out how to use those things to make our devices, right? Because then if I can just make one, literally just make one, I can make billions or trillions, right? They can be stamped across the wafer using those scanning photolithography tools with these perfect films that don't have any, particles or defects. We can take advantage of all of that machinery to make the photonics that we need to make scalable photonic integrated circuits for quantum networking purposes, okay? Now, what features do we want in our diamond-enabled quantum photonic integrated circuits? Okay, they're not the same as silicon photonics or microelectronics. Okay, but we're going to have to constrain ourselves to the materials and methods and all the things that they use if we want them to run in these foundries and really achieve the same kinds of scaling that are achieved with microelectronics and silicon photonics. Okay. So first, what do we want? The first thing we want, obviously, is intrinsic scalability. So I've been talking about it for like an hour and a half. Okay. We need to be able to heterogeneously integrate our diamond, right? Diamond is the key element. That's the thing that actually creates the quantum entanglement. And so if we can't figure out a way to integrate diamond into our circuits, it's kind of going to be a non-starter. Now, I'll tell you that the diamond is going to be one step that is not done in those foundries. We're going to heterogeneously integrate the diamond by other means, but it's just that one last step where we're going to put the diamond into our circuits. And we'll talk a little bit about how. But for everything else, we also need cryogenic compatibility. As I told you before, the diamonds have to be cold to do their little quantum magic, okay? And that means that everything else that is hosting the diamond and doing all the photonic connections and switching that we talked about and the photon detectors, they also have to be cold, okay? And so everything has to be able to work at temperatures that are close to absolute zero. Now, the diamonds, they only talk to very specific wavelengths. If it's a silicon vacancy, that wavelength is around 740 nanometers, okay? If it's the tin vacancy, it's around 620 nanometers. So they won't talk to any old light color, particularly they will only talk to colors of light that are absorbed by silicon. Okay, so what I mentioned before that that these foundries are making devices that use photonics, they're using silicon photonics. Silicon absorbs light that's shorter than around 1200 nanometers. Whatever. This is a little bit wonky, but it's an indirect bandgap material. So it doesn't just turn on abruptly like some semiconductors. It starts absorbing around 1150 nanometers or so and continues to get more and more absorptive. But by the time you get to the wavelengths that we want to use for diamond, it's very absorbing. Okay, so that's not going to work because we're just going to lose all our photons before we can do anything with them. So we can't use silicon for our waveguides. Okay, we're going to have to use some other materials that are CMOS compatible, that can be made in these foundries. Now, you already saw in the video that they can make SiO2, right? That was actually one of the materials they highlighted. There's another material called Si3N4, silicon nitride, okay? And that material has a higher index of refraction than SiO2 and can also be made in these foundries, okay? Not just can be, it is made. It's part of semiconductor manufacturing at large, okay? And so they can make silicon nitride and they can make silicon dioxide and they can do all this cool patterning we just talked about, okay? And so, so we're gonna try to use silicon nitride and silicon dioxide because those materials are transparent, highly transparent, at the wavelengths that we need, the 620 or 740 nanometers. They're essentially perfectly transparent at those wavelengths, okay? So we can make really good waveguides, like Shelby told you about, using those materials in CMOS foundries, okay? But we also need, I should go back a step. We also need to control, right? Remember I said that we need to create a pulse of light. We can't just shine the laser on the light on the color center forever. We have to create a very precise pulse of light and shine that on the diamond color center. And so we need some fast optical amplitude and phase modulation, meaning that we can turn the laser power on and off. We can control its phase, and we have to be able to do those things in this same platform. Okay, now that's going to be a problem, because silicon nitride and silicon dioxide don't really have any obvious properties, or at least they didn't, I would say, before, you know, our group and some others started doing this work, that would allow you to do that modulation, okay? Materials like silicon, if you're using silicon to modulate the amplitude of light or the power of light, you can actually just inject electrons into the silicon and use the electrons to control the amplitude and phase. So they use, you know, essentially electronic-based modulators, right? They're literally flowing charge in and out of the waveguides in order to control the amplitude and phase of light, okay? Materials like lithium niobate, okay, they use what are called, you know, generally what's called the electro-optic effect, okay? There's a material nonlinearity that means that an electric field you apply to the material will change the speed of light in the material. And that can produce phase modulation. If you put phase modulators together with beam splitters, you can make Mach-Zehnder interferometers, which are amplitude modulators. So you can make your amplitude and phase modulation using the electro-optic effect. But silicon nitride and silicon dioxide are not electro-optic, okay? And they will not permit, you know, they're insulators, right? So they will not permit charge to be put in and out of the material in order to do modulation. The only real way that people have been able to do this for the last, you know, whatever, 30 or 40 years that people have been doing integrated photonics with silicon nitride is to use temperature, okay? So if you change the temperature of silicon nitride and silicon dioxide, it will change the speed of light in those materials. Then that can work like an electro-optic effect, but you have to change the temperature. Now, the problem is we need our devices to be super cold, okay? So I can't heat them up in order to do the modulation. That would be a non-starter, okay? It also produces lots of other problems, like thermal modulation is very slow, so I can't produce pulses that are as fast as I need. It also dissipates a lot of heat. So if I put enough of these circuits on my chip, it'll just overwhelm the cooling power of my refrigerator that's keeping this thing at, you know, like below a Kelvin. And so that won't work either. So thermal modulation is out, okay? So we need some low power dissipation, fast modulation mechanism. And I'm going to tell you about that. But for now, we're just going to say, I don't know how we're going to do it, okay? We need some other stuff. We need integrated spin control, right? We need to apply those microwave pulses. We need integrated emission control, meaning that we need to be able to figure out how to integrate cavities and you know, use that Purcell enhancement to enhance the collection of photons into the channels they need to go in, right? That's why I was saying, like, the photons can't just spray out into free space. Every time I try to produce an entangled photon to do this entanglement swap operation we spent so much time talking about, the photon better go in the waveguide and go through the switch, right? Or I've just done all that for nothing, right? You know, so I want a very large fraction of the photons I produce to go into the channels I want, right? That's the emission control. We also need integrated electronics. Now, that we don't really talk much about this, but imagine I've got, you know, billions of, or whatever, let's say millions of these individual qubits in their little sockets where they're being controlled and caused to emit photons. And then each one of those goes through a switch, right? Well, that switch that is reconfiguring, that's going to be controlled by a voltage. which means I'm gonna have a lot of voltages I need to apply to my circuit. Okay, now on the left is a very nice paper, again, out of Dirk England's group. This is a device that uses 128 optical switches, basically. There's 128 voltages applied to it. And you can see, here is the photonic part of the device. Here is the electronic wire bonds that control the device, okay, on either side. So roughly, 75% or so of this device, okay, is just electronic wire bonds. And it turns out that as you scale, up the number of elements, that's going to happen on the interior, right? But the wire bonds all have to happen on the perimeter. So if you go to millions of channels for electronic control, what you're going to have is this like microscopic area in the center of an enormous, wafer full of wire bonds, right? It's impractical. So we need to make something that can integrate electronics where I can use a very small number of electrical inputs to control a very large number of channels on the device. Now that is exactly what microelectronics do, right? If you look in a microelectronic circuit, there are very few channels that go in on the perimeter. And then of course there are billions of transistors that are routed to, using electronic logic in the device, right? So I can use a relatively small number of inputs to control a very large number of electronic channels. So what that means is that if I can make my photonics process on, I'm making it in a CMOS foundry. If in addition, I can make it on top of the CMOS in a way that doesn't destroy the CMOS, now I've got integrated electronics too, right? Which is another enormous advantage of making these devices in CMOS compatible processes and CMOS fabricated processes, okay? And finally, we need our integrated detectors, right? Because it's not completely necessary. You can imagine maybe there are diffraction gratings that steer the photons off the chip, and you could have another chip sitting above it with just a bunch of detectors looking down. But the most practical way is to have those detectors actually on the chip as well. So these are all the things we need, right? And they're very different requirements than what you would need for silicon photonics or microelectronics. However, basically all of them are amenable, okay? I just want to spend 1 second to talk about materials like lithium niobate, because lithium niobate is an incredibly powerful material. Like I said, it's directly electro-optic, it's highly transparent at the wavelengths we need. There are some issues like it can't handle very high power, but that's not really an issue for the kinds of devices that we need to make. The biggest issue is just the scale of it, right? And the integration complexity. So lithium niobate, you can make what's called thin film lithium niobate. And again, if you listen to Marco Longcar's presentation earlier in the week, you would have heard a lot about this, but you can make it on roughly 6-inch wafers. It's a single layer of lithium niobate. You can put metals on the surface to control all the photonics. But there are a lot of issues with lithium niobate, right? It's an incredibly immature technology in comparison to the kinds of photonics you can make with silicon nitride and silicon dioxide, and using CMOS fabrication, because CMOS fabrication is leveraging $1 trillion a year industry that's existed for 70 years, right? It's the most sophisticated manufacturing that's ever been created by humans, okay? Lithium niobate is just sort of nascent, right? And they're doing amazing stuff, but it's like very problematic in some ways, like these sort of much smaller wafers. They have a high degree of variability for the film thickness across the wafer. That's very important if you're trying to make devices where you need the speed of light to be very constant over a large area. If you want all of your devices that you design to be identical, the film thickness matters. So if I make one device, in the center of the wafer, and then I move over an inch, and there the film thickness is 5 or 10% larger, that's not going to work. Okay, so the device over here is not going to work if the device over here works potentially, and that means that the yield is going to be low. So even though I can make incredible devices, I can't make lots of them on this wafer. And there are no facilities in the world that look like the TSMC facility for making lithium niobate. There is no facility with roboticized wafer carriers with 25 12-inch wafers at a time. Like none of these things exist for lithium niobate, and the level of integration is just significantly less complex. As I'll show you, the photonics process that we can do using CMOS fabrication allows us to have like these multiple levels of metal integrated up through the devices and down through the wafer. that allow us to route metal very efficiently to make all the electrical connections to the devices. You know, we can make the CMOS electronics underneath the wafers and connect them to them. There's a lot that we can do. They're just impossible, you know, with material like lithium niobate. So it's an amazing material in terms of its raw capabilities, its maturity, and fabrication, sophistication, and complexity is, you know, pales in comparison. So that's, you know, I think it's important to say, because it is probably the best alternative, right? And for just making like small numbers of devices, it can outcompete actually a lot of the devices that we're going to talk about. But the devices that we're going to talk about will win at scale, and that's really the point. Okay, so let's talk about, you know, how we're going to actually do this in a CMOS foundry. Okay, so first of all, the intrinsic scalability, we get it for free, right? That's the whole point. If we make these things in a CMOS foundry, we get the scalability. Okay. Now, for these visible wavelengths, we already talked a little bit about it, but we're just going to use our two CMOS fabricatable materials, silicon nitride and silicon dioxide. It turns out we can even make UV devices this way, like you know, with wavelengths that are shorter than blue wavelengths, and we can do that by using a material called alumina as the core of the waveguide. So that's Al2O3 rather than Si3N4. But for our purposes here, we're just really concerned with these visible wavelengths 620 and 740, and that's, you know, that works perfectly well with silicon nitride and alumina. Excuse me, silicon nitride and silicon dioxide. Now, what about this modulation mechanism? Okay, we said, you know, it's not electro-optic. You know, we can't do electronic modulation. So, so what are we going to do? Okay, well, I'll tell you about that on the next slide. But the integrated electronics, again, we talked about this. That's going to come for free, right? As long as you can build it on top without disturbing the transistors. What does it mean to not disturb the transistors? Well, it means that you can't get a temperature larger than some threshold where the electrons that have been doped into the silicon start to move around, basically, or you deform the metals, right? So it's really just it's sort of a process, a temperature budget, right? You can't, the rest of the things that you do to make your photonics can't raise the temperature of the wafers above, you know, say like 500 degrees C or so. Okay, and that turns out that's going to be the case. And so that's what's called post-CMOS fabricatable, meaning that you can make it on top of CMOS without disturbing the CMOS. And that's going to allow us to directly integrate with electronics. Okay, cryogenic compatibility. It's not really obvious that our devices will be cryogenically compatible, but I'll tell you they will be. Okay, now the materials are all cryogenically compatible, and this modulation mechanism that we're going to talk about is also cryogenically compatible. So we are going to have cryogenic compatibility. Integrated detectors. So it turns out that there's a device, again, we don't have a lot of time to talk about this, but there's a device called a superconducting nanowire single photon detector. And those devices are essentially very, very thin strips of superconducting metal that you put on top of the waveguides, and they can allow you to detect single photons because a single photon will be absorbed by the metal, and that little tiny increase in temperature takes the metal from superconducting state to a non-superconducting state, meaning that if I'm applying a current, I will measure essentially no voltage drop let's say this. If I'm applying a voltage, I'll be producing a current that will flow with very small resistance because it's superconducting. When it changes to its non-superconducting state, it will all of a sudden have a resistance and there'll be a big voltage drop, a smaller current, and I can detect those things, right? So people have used those to make superconducting nanowire single photon detectors for probably, I don't know, maybe it's like 15 years now or so. And so they are made with materials that are entirely CMOS compatible. Excuse me, it's entirely CMOS compatible. The particular materials you need, something like niobium. So niobium is a superconducting metal that you can use for what are, you know, SNSPD, superconducting nanowire single photon detectors, or even the most complex and best material typically, which is a mixture of niobium, titanium, and nitrogens. Niobium tinitride is also completely CMOS compatible. So those materials are available in the CMOS foundry, so we can make our detectors. And then finally, you know, we need our integrated quantum resource generators, and then we're going to do that by heterogeneous integration. I'll tell you a little bit about a few slides from now. Okay, so how about this modulation mechanism? Okay, well, yeah, here's a paper from my PhD. the paper describes the way that strain can interact with optical resonators. So you know, little areas on a chip where you can store photons through a mechanism called optomechanical modulation. Okay. Now, optomechanical modulation has sort of two parts to it. Okay. The first part is that if I take a material, say like silicon nitride or silicon dioxide, or really any material, but I want to focus on those. If I take it, let's say I had a big chunk of it, and I squeeze it together, okay? If I were shining a laser through that material, what I would see is when I squeezed it, it would actually change the speed of light through the material, okay? You can measure that by measuring the phase that the light accumulates as it goes across. So, so you can change the speed of light of a material by just squeezing a big chunk of it, okay? That's called the photoelastic effect, and pretty much all materials have a photoelastic property. You know, they have some coefficient that relates how much speed of light change you get per unit strain. Okay. Now, there's a second part of it, which is called the moving boundary effect. Now, for this one, you have to imagine that light is moving through this tiny little wavelength scale waveguide. So that the waveguide is not much bigger than the wavelength of light. If I deform the waveguide by squeezing on it, you know, straining it, just like I, you know, did with the big chunk, but now I'm imagining this like tiny little one that's getting strained, you know, this waveguide that's getting strained, it's actually changing its shape. And it turns out that the speed of light going through a waveguide is determined by its shape, okay? When they're a wavelength sort of in scale, if you change the shape a little bit, you can drastically change the speed of light, okay? By drastically, I mean maybe like, you know, by a part in 1,000 or part in 10,000 or something like that. But that turns out that's pretty drastic. That means that in about 10,000 wavelengths, I'll accumulate a pi phase shift, which is enough to completely destructively interfere the light, right? With that, make my amplitude modulator. So, you know, how long is 10,000 wavelengths? Well, it's about, you know, something like less than 10,000 microns, right? So, so about a centimeter or something like that, right? So, so in small length scales on my chip, I can apply strain, and through these two effects, the photoelastic effect and the moving boundary effect, which together we call the optomechanical, you know, effect, I can produce the phase modulation I need by changing the speed of light, and thus create the amplitude and phase modulation I need to perform my entanglement gate operations, right? So, so what? The thing that we're missing still is a way to actually produce that strain, right? I have a bunch of little switches and stuff, right, that I want to control individually. And so I can't just like squeeze the whole wafer, right? So how do I make a bunch of little actuators that can strain individual parts of my chip at a time? Well, we're going to do that through what's called the piezoelectric effect. Okay, so again, this is you know, we have like an hour and 10 minutes left, so I don't have a lot of time to talk about the piezoelectric effect. But what the piezoelectric effect is in certain materials, okay, which have a particular property called a lack of inversion symmetry. I mean, so what it means, so I'll show you the material we're going to use. This is called aluminum nitride. It's a lattice of aluminum and nitrogen atoms. It turns out that this is a piezoelectric material that can be deposited inside of one of these CMOS foundries, okay? This lack of inversion center of symmetry, what it means is that if I were to mirror the lattice about a particular plane here, I would not get back the same structure. So if you take a material like you know, diamond, for example, at these particular planes in the unit cell of the lattice, you know, mirroring it gets you back the same exact lattice. This, you know, you won't bother showing you, but you can show that this thing has mirror planes where there is you do not get back the same lattice. So it lacks what's called an inversion center of symmetry, and that ultimately means that that the material can undergo this coupling between electric fields and strain, meaning that if I strain the material, I will build up a net electric field. Okay, charge will basically move inside the lattice such that there's a net electric field produced inside. Or alternatively, if I apply an electric field, it will actually strain. Okay, so what does that mean? That means that now I have a strain actuator with this material. I can apply electric fields and the material will actually strain itself. Okay, so if I can put that material in direct contact with our waveguides, then we can now strain our waveguides by using little individually patterned, actuators made in this aluminum nitride material that are connected with our metal traces, like in the CMOS wafers, and then they just have to connect to the optical waveguides. Now I've got everything I need. Okay, so I can apply voltages, using my integrated electronics to strain the waveguides and produce the modulation that I need. Okay, so these are actual wafers made at Sandia National Laboratories, right? So Sandia, like I said, I have a joint appointment at Sandia National Labs, and so we have developed a process using the CMOS foundry at Sandia that they use to make microelectronic circuits for defense applications. We have developed processes for making this, taking that CMOS foundry, which is not quite as sophisticated as the TSMC foundry I showed you, but it's along the same lines, right? It's sort of it's an older facility. Okay, so it's not as sophisticated as like what you would see in the TSMC video, but it still can make very sophisticated microelectronic circuits, just not quite as small. Okay, but we've been able to take those tools and those materials in that CMOS foundry and build these wafers at scale. So this is an 8-inch wafer. Okay, that 8-inch wafer, you can actually see remember in the TSMC video, it showed the sort of serial projection of the photomasks across the wafer being done one at a time. Well, you can see those actually here. You can see there's a little pattern here that's repeated across the wafer, across this 8-inch wafer about 40 times or so. Okay, that is this little die here, this 1-inch by 1-inch roughly die, and on that 1-inch by 1-inch die, there are these little individual photonic circuits. Some of them big, some of them small, but the smallest ones are the head of a pin would be astronomically large in comparison, right? So we can make our photonic devices. Now let's talk a little bit about kind of how they actually work. So remember in the TSMC video, they talked about building up these layers of materials sequentially one by one, right? You deposit a film, you deposit photoresist, you expose the photoresist with your photomask with the actual pattern. That you rinse away the photoresist that leaves behind just the stuff that you didn't expose. Then you do something to etch the material now that is, the etch is only stopped where the photoresist is remaining. So then you transfer the negative of your pattern into your material, and then you rinse away the photoresist, you deposit something else, planarize it, and you do it again, right? So that's exactly what we're doing here. But now we're building a circuit to control light. Okay, so we have our first metal layer. We have it's probably inefficient to walk you through the entire process, but this uses 11 photomasks, right? They talked about the number of different photomasks and the complexity. So just to make the photonics takes us about, well, not just the photonics, but the photonics plus the electronic routing for the photonics takes us about 11 mask levels. But that's all we need to sort of make all the things. This is an example of one of the devices. Okay, so this is a paper we published a couple of years ago. This particular device. So we're going to start with a phase shifter, right? And then we're going to build our phase shifter into a Mach-Zehnder interferometer that will make a Mach-Zehnder modulator. Okay, so the cross section of the device looks like this. It's got a silicon nitride waveguide core, just like we've been talking about. That's surrounded by silicon dioxide. Okay, the silicon dioxide is just thick enough that the little tail of this mode that would evanescently decay, you know, exponentially decay away. It's just thick enough that the silicon nitride and the light living inside of it won't talk to the metal here, because this metal would be very lossy for the light going through the waveguide. So it's just thick enough, about 700 nanometers or so. You know, something like you know, 1,000 nanometers is 100 times thinner than the diameter of your hair. This is about 700 nanometers, right? So it's a little bit thinner than 100 times thinner than the diameter of your hair. So very, very thin layers, right? The waveguide layer is about 300 nanometers thick, right? So almost 1,000 times thinner than the diameter of your hair. Then, so you have this metal here. This is our piezoelectric aluminum nitride layer that's gonna, when I apply a voltage from the top electrode to the bottom electrode and apply this field across the aluminum nitride, it's gonna produce the strain, okay? That's what's sort of shown here. It's like, you know, sort of showing you like if I hooked a battery up to it, to the two electrodes here, it would produce the strain, right? So this is our actuator stack, aluminum, aluminum nitride, aluminum. And that's pretty much it, right? So, so we have all the things we need. So when I apply voltage across these two plates, it's gonna strain the aluminum nitride. The strain of the aluminum nitride is gonna couple to strain in the silicon nitride and silicon dioxide, because they're just sitting, you know, like far, you know, smaller than a hair's width away from that actuator. And that strain is gonna strain the silicon nitride, and that strain in the silicon nitride is gonna change the speed of light. Over some length, that's gonna change the phase and allow me to make, you know, to change basically like, okay, so this is the circuit. So I have light. Let me put my laser pen back on. No, I want laser pen. No, I just want pen.
You're doing great.
Pen, okay. Not laser pen, pen. So if I have light that comes in on this channel here, okay, it's gonna go through this directional coupler, okay? And that means that it'll get split in half. Okay, so now I've got light traveling in that path and light traveling in that path, okay? So if I don't strain the material after they come back together, maybe they'll be constructively interfering so that the light all goes out, say, this channel, okay? So I put light in the top channel, it came out the other top channel. If I can change the phase of light just by half a wavelength, okay? Pi, right? Just half a wavelength worth of phase delay will change the light from coming all out of this channel to all out of the bottom channel. Or I can create any arbitrary combination of top plus bottom channel on the output, right? So I can choose what fraction of the light goes out each of those. And I can put another phase shifter on the output and also change its phase. So this is a device that allows me with two voltages, controlling the strain of this waveguide and this waveguide essentially, to create arbitrary amplitude and phase on the output, okay? So I could just say, look at this one, look at this output port. And now if I make all the light go out over here, you know, there's no light coming out here, or I can make all the light come out up here. So I can turn the light completely off or make it completely on, and I can control its phase. So I can do all the things I need. Now, I can also do that very fast. I can turns out with this architecture, I can use that piezoelectric strain to turn the light on and off in just a few nanoseconds, right? A few billionths of a second, which is plenty fast to perform the operations I need on the color centers to make them emit the photons, okay? They consume a very small amount of power, about a billionth of a watt, okay, which is small enough that you can make a lot of these circuits and it will not overwhelm your cooling system. They also don't like talk to each other through their dissipated heat, right? You wouldn't want to, you know, turn a voltage on in this device and it gets so hot that the device next to it also sort of gets disturbed, right? So they have low crosstalk. So it meets all these really stringent specifications. I'll go ahead and skip this. Just say a little bit about this heterogeneous integration of diamond. Okay, so if I go back to here, okay, you can see the silicon nitride is really close to that top surface. Okay, Well, it turns out I can actually just, through those, processes we described, we can etch away and actually remove all of the silicon dioxide over the top of that thing, okay? And if I do that, I can lay diamond down across the top of it, okay? So I can have actually a waveguide fabricated out of diamond on a different chip, and I can place the diamond down on top of the silicon nitride on this circuit, and that allows me to actually couple light from the silicon nitride waveguides into the diamond and back with pretty high efficiency. And these are papers, if you'd like, you can read about examples of this. There are also lots of papers from Dirk Anglin's group that you can read about where they've demonstrated this integrated control, heterogeneous integration of diamond and then photonic sourcing and collection of single photons. So these are joint publications by our group, but you can read lots of papers from Dirk's group. So it's a well-established technique, but the idea is I have a diamond chip that's completely separate from all of the CMOS processing we've been talking about to make the photonics. Okay, but on that chip, I basically make a little array of waveguides, and then you can essentially pick them up and put them down on top of the photonic integrated circuit that you made in the CMOS foundry, and that's all you need to make all the functionality that we've talked about. Okay, so I think I'm gonna skip the rest of this. And I think, so that's a good time for like a very short break. And then Eileen and Jake will talk about some specific devices that they have been working on for the rest of the class, I think. If we have time, I will present some slides that one of my other students, Mayank, made. He wasn't able to attend today, but I'll present his slides if we have extra time. So this is maybe a good time to ask if anybody has any questions. You can.
But there've been some in the chat.
Oh, okay.
But...
Let's see, then how do I read them?
Oh, well, I think there were ones that I knew the answer to. But...
Oh, so you just replied?
Yeah.
Cool, okay. How do I see them though? I can't see them at all.
Q&A.
The bottom.
Oh,
Yeah.
Q&A.
There.
No open questions, okay. So if you would like to ask, let's take a 5-minute break. We'll come back. We'll start at 37 after. Whatever time zone you're in, it will be 37 after, unless you're in India, in which case it could be a half an hour later than that. But I'm not aware of any other countries that have a half time zone difference. So, but if you're in one, do the math. Yeah, so we'll start at 37 after in the US time zones, say. Yeah, but in the meantime, I'm happy to answer any questions if people want to pop them into the chat. Ooh, there's a dismissed question. Did we have a heckler?
No, that was,
Oh,
It
okay,
just wasn't a question.
okay.
I didn't realize you worked with Carrie Bahala. That makes a lot of sense now. Yeah.
Okay, well, since we have 5 minutes and there don't seem to be any questions, I'm gonna get myself some more coffee.
Oh, I was gonna
Sharing, am I?
I was gonna say, you're not sharing. I was gonna share the cover again.
Okay, yeah, do that. And how do I stop presenting?
Does it still show that up there? Sorry, no, my thing.
Yeah, you see your slide.
Okay. I just, cause like whenever I move, their like screen sharing is paused and I'm like, I don't know what that means. But...
Anybody else want?
I'm okay, thank you. Can you just take coffee here? Is that a thing?
I don't drink.
Fair. Not usually either, but if it's free around me, I would.
That is fair enough. I definitely had coffee this
Yeah.
Okay. Welcome back, everyone. I'm a minute late, I apologize. All right, so we have about 40 minutes? No, 50 minutes. And in that time, we are going to, like I said before, we're going to have Jake and Eileen, and perhaps I'll present my own slides. They're going to tell you about some of the more advanced type of devices that we make in this integrated photonics platform, built at scale in a CMOS foundry, all the stuff we've been talking about. They're going to tell you about some of the more advanced devices that we're working on. This information is going to be pretty technically dense. But, so obviously, don't feel like if you're not completely following along, that it's a problem. I think hopefully you'll just be able to see kind of like, some of the more advanced functionalities we can make and how cool they are. Not necessarily feeling like you need to follow every single detail. But I will say that both Jake and Eileen are really fantastic presenters. And so I do feel like, they'll be able to walk you through it in a way that you'll understand most of the details. All that being said, I'm going to be sitting here on my laptop. So if you'd like to post questions in the Q&A while they're presenting, if there's something you don't understand, feel free and I'll try to answer them, without interrupting them. Or maybe if I think that it's something that, is really important, I'll maybe interrupt them and ask them to explain. Okay, so I think we can go ahead and start with Eileen. You might want to move that mic like real close to you, especially with the mask on. It might be. It's, yeah, I don't know. Like it seems like they should have more stretch.
I'll just try to yell.
One of us.
Okay, cool.
Can we just do an audio check?
Hey Brianna, can you hear me?
Yeah, you sound fine.
Okay,
Great.
perfect.
Thanks, Brandon.
Thank you. All right.
Wait, sorry. I need to leave my I'm leaving it unmuted because that's the room mic. Yeah. Okay.
Yeah.
Go ahead.
Cool. Yeah, so I'm Eileen. I'm a third-year grad student in math group here at the University of Arizona, and I'll be talking about the project that we've been working on, which is the MEMS-enabled control of all photonic and spin degrees of freedom of an artificial atom and a microdisc resonator, which I know is a lot of words, but we'll break that all down. Just really quick, my background, I'm originally from Madison, Wisconsin. I did my undergrad in philosophy and physics at Carnegie Mellon University in Pittsburgh. After undergrad, I worked for 2 years on these like bulk free space quantum optics experiments. And now I'm doing my PhD here. Okay, so it's pretty cool because actually what Matt and Shelby have both talked about earlier today have really filled in some of the background for this talk. So just to give a quick refresher to a couple of hours ago, we're in the CQ and we're using these artificial atoms in diamond. So first of all, artificial atoms exist in lots of materials like silicon, silicon carbide, 2D materials, not just in diamond, but for our design implementation, for now, we've chosen diamond. So these artificial atoms are point defects in the diamond carbon lattice structure. So diamond is just a bunch of carbon atoms arranged in a specific way. And these artificial atoms happen when two adjacent carbon atoms in the lattice are missing, and we have an atom of some other species in the lattice at that location. So for example, here are two important ones. Maybe I should turn on my laser pointer. How do you do that? Okay. Yeah, so, okay, perfect. So this one here is the nitrogen vacancy center in diamond. You can see that this happens when the two adjacent carbon atoms are missing and a nitrogen atom sits at one of the two carbon vacant sites. For this talk, I'll be talking more about this one, the silicon vacancy center in diamond. This actually applies to, like this geometry holds for a lot of different vacancy centers. They're called the group 4 vacancy centers. So in addition to silicon, that's tin, germanium, and lead. But what happens here is we have these two missing carbon atoms right next to each other in the lattice, and instead we have a silicon atom that sits in between the two vacant sites, so not at one of the vacant sites, like in the nitrogen vacancy center. Oh, and these artificial atoms, they're called artificial atoms because they also exhibit like energy level structures just as natural atoms do. And these artificial atoms in diamond are leading single photon emitters and qubit and quantum memory candidates due to their long coherence time. So they're able to store information for a long time. They're optically addressable, so we can do our initialization and readout using optical pulses. And they also have coupling to nearby nuclear spins with even longer coherence time, like on the order of minutes. Okay, and so Matt's already shown this picture before, which is great. As we've already talked about, this is great because in things for like quantum computing, we can use these artificial atoms to create a cluster state for measurement-based quantum computing, which is a method of doing scalable on-chip quantum computing. And we can also use these as vacancy centers in diamond as qubits and quantum network nodes. And this work is all really exciting, but it does help us illustrate some challenges of scalability with these diamond-only devices. So these vacancy centers exhibit a natural heterogeneity in their emission frequency. And so if we want to take two distinct emitters and interfere their photons, they have to be identical in every way, including their emission frequency. And so when we have these devices, that means we have a lot of vacancy centers and devices to sift through before we find two that just happen to be naturally similar, two or more that are naturally similar. And in addition, there's been some difficulty in isolating single qubits using a microwave drive to do the qubit control. So to really multiplex diamond vacancy centers for quantum computing or networking on chip, we have to have ways of controlling and addressing individual vacancy centers. Okay, so like I said, diamond color centers, not all naturally identical. This is due to a variety of factors, including local strain in the carbon lattice where the vacancy happens to sit, their fabrication, and their proximity to surfaces, as they can be sensitive to surface roughness. So the tuning mechanisms that we need is we have to be able to control the emitted photon frequency, and if we embed them into a cavity, we have to be able to control the cavity resonance, both their central frequency and the spectral profile. And so that means we have to be able to tune photons from distinguishable emitters to be identical in order to interfere them with the same central frequency and same spectral profile. So this shows some work from some of our collaborators who are able to demonstrate strain tuning of, in this case, a twin vacancy center by over 20 gigahertz. In addition, as Shelby talked about earlier, when we put these into a cavity, and we need to be able to tune the cavity resonance to be simultaneously resonant with the emitter frequency in order to take advantage of the Purcell enhancement, which helps us increase our collection efficiency of these emitted photons. And finally, if we want to interfere single photons, two photons from distinct emitters have to reach, say, like a beam splitter at the same time. Okay, so far, a lot of these individual control mechanisms have been demonstrated using this diamond quantum microchiplet device, which is shown here. This is a device that's fabricated out of diamond. This is a waveguide-based device, so no cavity, where the emitters are located in the waveguides of this device. And so using these devices, we've demonstrated integrated microwave line for spin qubit control using like a microwave drive, and also strain tuning of the quantum emitters in the diamond waveguides. In the piezoelectric platform that Matt just talked about, we also have been able to demonstrate these large displacement MEMS cantilevers, which will become important in a minute, and we'll talk about that. And also other groups have been able to demonstrate acoustic control of the spin qubit. So instead of using a microwave drive to drive the spin qubit transition, using dynamic strain to do that instead. And so in this work, we're moving toward a cavity-based approach to enhance photon collection efficiency through leveraging the Purcell effect, and then also integrating these cavities with photonic integrated circuits that allow for control over all opticals and spin degrees of freedom in a single socket. Okay, so our choice of vacancy center for this are the group 4 diamond vacancy centers, including the silicon vacancy center. This is kind of the structure of what that looks like, the silicon in between the two vacant sites in the carbon lattice. And we can see that this structure is inversion symmetric, which makes it insensitive to the first order Stark effect, which is important because that helps us maintain optical coherence in nanostructures. We also have an electronic spin qubit with coupling to nuclear spins, and also optical transitions that allows readout of the spin quantum number. And our choice of cavity is the microdisc resonator. So diamond is a very difficult material to fabricate, but the geometry, which is of a microdisc, which is pretty simple, it's just a circle, is relatively easy to fabricate in diamond as opposed to say like a photonic crystal cavity with lots of little holes. And microdisc cavities can also be fabricated with really high quality factors. For example, this one has a Q of over 300,000. And to increase the Purcell enhancement, as Shelby mentioned earlier, it's kind of, we want to maximize the Q while decreasing the mode volume. And however, while the microdisc resonator has a larger mode volume than, say, photonic crystal cavities, the mode volume is still relatively small, but the Qs are high enough to still ensure a large Purcell enhancement. Okay, so this is all great, but how do we actually make a system that can do all of this? So here's where we're talking about heterogeneous integration, as Matt alluded to earlier. So on the one hand, we have our photonic integrated circuit that's fabricated in this platform. We use a silicon nitride core, a waveguide core with a silicon dioxide cladding. We have aluminum electrodes that allow us to, and an aluminum nitride as our piezoelectric layer. So when we apply voltage to the aluminum nitride, that causes strain and other things. One thing that is also really cool about this platform is that we can make these structures that are undercut. So basically released from the substrate in certain areas that allow them to be very mechanically compliant. So these can basically freely move. On the other hand, we have our diamond, which is fabricated separately on a separate diamond chip. And what we do is we go in with a little tungsten probe, we take the diamond micro structure off the diamond parent chip, and we put it down on our photonic integrated circuit, wherever it needs to go. And so we've been talking a lot about scalability, and this sounds like the least scalable thing in the world, where you go in one at a time and you take diamond, you put it down. But there are more scalable ways of doing this. For example, this is the lock and release method, where we are able to heterogeneously integrate lots of diamond structures at the same time. Excuse me. And so we can work, these devices can be designed as well to work with the lock and release. Okay, and so this is a quick device overview. We've been calling it the Uber socket colloquially in the group, where we have here the diamond microdisc is firmly attached to the photonic integrated circuit, the socket, and the emitter is of course located in the diamond microdisc. The diamond microdisc resonator is a whispering gallery mode resonator. So this is what the cavity mode looks like from a top-down view. We can see that the mode resides pretty much on the outside edge of the cavity. Sitting below the diamond microdisc is a piezoelectric strain actuator. So when we apply voltage to the strain actuator, that causes the piezoelectric aluminum nitride layer to strain, which causes the attached microdisc to strain as well. And that strain causes the embedded color center to change its emission frequency. In addition to that, we can use this piezoelectric strain actuator to target an acoustic mode.
Sorry, is that on your screen, Ellen? You can't see it or what?
No, sorry, I got distracted. So we can also use this piezoelectric actuator to target a mechanical eigenmode of the device, allowing us to perform the acoustic spin qubit control as well, instead of having to use a microwave line. So as I said earlier, we've been able to demonstrate these large displacement MEMS cantilevers in this platform as well. And so we're using one of these as a cavity mode tuning cantilever in order to tune the cavity mode frequency to be simultaneously resonant with the emitter frequency. And then finally, we're using a cantilever phase shifter to do tuning of the temporal profile of the photon. Okay, so now getting into each of these device capabilities in detail. As I said before, to do tuning of the color center frequencies, we use a piezoelectric strain actuator that's located below the disc. So that's shown here, a simulation of that is shown here. So I'm applying voltage to the aluminum nitride layer, which causes the entire geometry to change and strain the diamond where the emitter is located as well. And so using this, we simulate up to 650 megahertz per volt of frequency tuning of a silicon vacancy in a microdisc. The scale of tuning that we need generally is around 15 gigahertz. So this is plenty so it's plenty to be able to compensate for that, given that we can apply around 100 to 150 volts before the devices start to fade. And so this should be sufficient to compensate the heterogeneity of different silicon vacancy centers to be able to tune distinct emitters to be identical. However, strain tuning the diamond color center also tunes the cavity mode frequency of the diamond microdisc through the photoelastic effect by 140 megahertz per volt as well. So this is not really desired, because when we want the cavity mode and the emitter frequency to be the same. And so that necessitates an independent cavity mode tuning mechanism. So for example, suppose we have two Uber sockets, each with an integrated microdisc hosting vacancy centers with different wavelengths. However, in Uber socket 1, we have the cavity and the emitter. They're both simultaneously resonant at the desired frequency F0. But in Uber socket 2, where the cavity is already on resonance, the emitter is slightly detuned. So luckily, what we can do is we can apply voltage to the strain actuator to correct the emitter frequency back to F naught. But through the photoelastic effect, now we've detuned the cavity. And so we have to have a way of tuning the cavity frequency back to the desired frequency. And so to do that, we use a MEMS cantilever to perturb the whispering gallery mode by introducing dielectric material in the evanescent tail of the mode. So the cantilever looks like this. We have silicon dioxide with an aluminum nitride layer. So applying voltage to the aluminum nitride layer causes the entire cantilever to deflect out of plane. The whole structure is undercut. And so that's what that looks like here. Ignore this box. That's just like a simulation thing that I have for simulating an air box. But basically here we have the diamond where the mode would sit at the edge, and by applying voltage to the cantilever, we cause the diamond to see different amounts of material. And that changes its effective mode index, which changes its frequency. And using this method, the socket can independently tune the cavity mode by 120 gigahertz, which is more than sufficient to correct for the photoelastic tuning caused by the strain tuning of the color center, but also sufficient to compensate for expected fabrication variation of the diamond microitis cavity itself. The socket also will allow for spin qubit control using dynamic strain. So for example, here, this is the electronic level structure of a silicon vacancy center where the spin qubit is located here. We have this mechanical mode with a frequency of around 2 gigahertz. The splitting of the qubit transition is usually set to be over 1 gigahertz, anywhere between like 2 to 4 gigahertz. So here we have a mechanical mode with a frequency of 2 gigahertz that would be sufficient to drive this transition. And through simulation, we expect a maximum spin phonon coupling of 19 megahertz. It's pretty high. And then finally, we also have control over the waveguide cavity and coupling rate through interferometric coupling. So here what we have is the diamond microdisk is coupled to the photonic integrated circuit at 2 points. So once here at the top and once here at the bottom with a phase shifter in between. So by setting the phase shift of the part of the photon that couples in at the top, we can control how it interferes with the part that couples in at the bottom. And simulations show a single waveguide coupling rate of 650 gigahertz, allowing for us to tune the coupling rate from 0 to twice that. So 0 being complete destructive interference to twice that, which is constructive interference. So 0 to 1.3 terahertz, which is limited by the loss in the phase shifter between the coupling regions. But even if we're unable to get it completely down to 0, as long as we can set different sockets to be the same, that's basically the name of the game. Okay, cool. So yeah, this device has been fabricated in the piezo optomechanical photonic integrated circuit platform developed at Syndia. And in this platform, we have tons of other things like piezoelectrically actuated cantilever Mach-Zehnder interferometers. We have these what's called ski jump cantilevers that can do on and off chip coupling, edge coupling, even from the middle of a chip, and demonstrated tons of other things like ultra low loss waveguides that Matt might talk about on the first time. We also have strain tuning color centers, integrated microwave drives, integrated SNS PDs, integrated photonic probes, tunable directional couplers, and acousto-optic modulators that Jake will talk about in a second. Okay, so the devices have been fabricated at Syndia National Labs, and here's a micrograph of what that looks like, showing all of the different components. Here is an SEM of the cavity tuning cantilever, and we can see that it's actually deflected out of plane upon release. So it's been completely released from the substrate, except for the side that's like still being held down. And we can see that it does move relative to the diamond. And then here's an SEM of the full Uber sockets upon release, and we can see that by the curling of the phase shifters, that all the phase shifters have also been released at the bottom. Okay, so it's cool. Now we have these devices, we have some diamond, and so now what we have to do is work toward characterizing these diamond microchiplets and the devices. And so to do that, we've been working on building a free space laser scanning and excitation setup of these color centers in a diamond nanostructure. So here's just kind of a first pass test that I did with a laser scanning system, where I just scanned a random chip feature, in this case, this 6 on a chip that I found, and I found that I was able to scan that feature back. So it's cool, but what we actually want to do is be able to see, kind of locate where the color centers are in a diamond structure. So here, for example, is a camera image of a chiplet with SIV. So this is like the waveguide based chiplet that I showed before. And my scanned image, of course, this setup needs more work, and the alignment could definitely be optimized, and probably the filtering as well. But here we can see kind of the rough outline of the frame of the device plus some structure where the waveguides. In addition to that, we've also started testing the actual devices, checking the actuation of cantilevers, of the cavity tuning cantilever and the phase shifter cantilever. Also, we want to check the piezoelectric strain tuning of a color center, and then also we want to couple light on chip through grading couplers. So here is a microscope image showing the deflection of the cantilever out of plane. So focusing the microscope on the strain actuator here shows that the tip of the cantilever, which is here, is out of focus. And then changing the focus of the microscope tells us how far the cantilever is bent out of plane. Yeah, so that's kind of the work that I've been working on now. In conclusion, the Uber socket is a single device that allows for control over all optical and spin degrees of freedom of a silicon vacancy center in a diamond microdisc. So that gives us up to 65 gigahertz of strain tuning of a silicon vacancy center, which should be enough to compensate for the natural heterogeneity of silicon vacancy centers. We get up to 125 gigahertz independent tuning of the cavity mode to be able to ensure that our cavity mode and our emitter frequency can be simultaneously resonant. We have tuning of the waveguide cavity coupling rate from 0 to 1.3 terahertz, and also electronic and nuclear spin qubit control through dynamic state. So the next steps there are just testing and characterization of the microdiscs, the embedded color centers, and the actuation of the different mechanisms of the socket. And yeah, we want to take measurements of all of that. Yeah, that's it.
Okay, great. Thanks, Eileen. I was just reading the question. So trying to get that.
Yeah, I can do that one.
Okay, great. So are there any questions about Eileen's presentation? Well, if you do have questions, feel free to put them in the chat and we can answer asynchronously. We are now going to move to Jake Friedman's presentation.
Okay, hi, I'm Jake. First I'll give a little background about myself. I graduated from Colgate University a few years ago now, where I studied physics and math and did some optical physics research with my advisor, Pico Galvez. And oh yeah, here's a picture of me doing physics in the physics building. And now I'm a PhD student in Matt's group, where I work on projects that are for, among other things, the Center for Quantum Networks and Quantum Moonshot and QSA, mostly focused on integrated photonics for quantum computation. So the first thing, what I want to talk about eventually is a device that performs quantum control, but first I'll give a little background on what it is exactly we're trying to control with the device. So there are a bunch of different candidates to encode a qubit for quantum computing, but popular choice are atoms, ions, and atom-like structures, like the silicon vacancy center that's been discussed today. So on the bottom left corner of this slide is a table showing some of the popular choices for qubits. Silicon vacancy center has a wavelength of 700, has a transition at a wavelength of 737 nanometers, and then you can encode a qubit in the spin of the electron, which Eileen discussed in her presentation, can be controlled with microwaves, even acoustic waves, and as I'll discuss in this presentation, with light as well. And then there are just some other atoms and ions listed that are used as qubits, and you can see they also have optical transitions and gigahertz frequency qubit transitions. So how are these qubits controlled in practice? Well, on the left-hand side of this slide is a photo of a setup to control qubits in the neutral atom array at Harvard. You can see it's very complex, and in the center of this whole mess somewhere, there's a vacuum cell with that would have around 100 atoms in it that form the quantum computer. And as we've talked about today, eventually quantum computers are going to need a lot more qubits than just 100, and therefore the controlling optics and electronics are going to need to become a lot more scalable than this table has here. So what I've already mentioned is you can control these gigahertz frequency transitions in qubits with microwaves directly, because microwaves have that exact frequency of the transition and therefore can drive Rabi oscillations between the ground and excited state of the qubit. However, there's a problem because in these arrays, or for trapped ions in the chain of ions, or silicon vacancy centers where they're all embedded into a diamond chiplet with a small spacing, many per square millimeter, is that the microwaves cannot be focused down to a small enough spot size such that they only interact with a single qubit when you're trying to control a single qubit. So to illustrate this, I'm showing an array of atoms, ions, or silicon vacancy centers, whichever you'd like to imagine, that are spaced by about 5 microns, which would be typical, at least for a neutral atom array. And so if you tried to drive a qubit rotation with a microwave in this array, it would sort of have a big spot size that covers all of the atoms, and you would deleteriously drive transitions in atoms or ions that you're not trying to control. So instead, it would be nice if you could use a laser that has an optical wavelength of, let's say, like 700 nanometers, and then you can focus the spot size down to a tiny spot that only would focus on one atom, one qubit. But the problem is that like that doesn't match the transition frequency. The transition frequency is like in the gigahertz range, and this would be in the hundreds of terahertz. So to get around that, people use what's called Raman control of atoms, ions, or silicon vacancy spins, where instead of using a single frequency laser or a direct microwave drive, you have 2 laser beams whose frequency is separated by the transition frequency. And then you can show that this will effectively act like a single, it will act similarly to just driving it directly with the microwave at the exact transition frequency. So the key ingredient to doing this Raman control is that you have a laser beam, and then you have one that's separated by exactly the qubit transition frequency from that initial laser beam. And how that's accomplished in practice regularly is you start with a laser that's at a frequency omega, and then you pass it through an electro-optic modulator, which we've also mentioned today that there are some materials that exhibit the property that when an electric field is present in them, that it modifies the material's refractive index. So if you have a crystal box of one such of these materials and you make there be a sinusoidally varying electric field within the crystal, then its index of refraction will also vary sinusoidally. And if light is propagating through that crystal while that's happening, it will accumulate a sinusoidally varying phase. So that's what these equations are representing. After we've passed through this electro-optic modulator, we now have a sinusoidally varying phase with an amplitude called the modulation depth of alpha. And that will just be related to how strong the electric field is in the crystal and also how strong its electro-optic coefficients are. But the point is that after you do this sinusoidal phase modulation, the field can be rewritten in this way, where it's been decomposed into its frequency components just with by a Fourier series. So, but it elucidates what the effect of sinusoidal phase modulation is, and that is to produce sidebands in frequency space on the original carrier that are spaced by integer multiples of the modulation frequency. So this omega here is mislabeled. It should just be the same capital omega as here. But this equation shows that there are an infinity of sidebands that are each spaced by integer multiples of the modulation frequency, and which have weights given by Bessel functions evaluated at the modulation depth. Just below this equation, I've shown what these Bessel functions sort of behave like as a function of the modulation depth. So as we turn up the modulation, the power in the various frequency components follows these curves. So at first, when you don't modulate at all, not all of the light is in the original carrier frequency. That's no surprise. But then as you turn up the modulation depth, more and more light is being transferred into the sidebands. And just remember that the key thing we're trying to accomplish here is just create light at a frequency shifted by the qubit transition frequency to do the Raman control I talked about on the previous slide. So essentially, I mean, there's some caveats to this, but what you want is to get a lot of light into this purple curve. So you want modulation depth probably somewhere between 1 and 2. And there are commercial devices you can buy that do exactly this, that are tailored to specific qubits. An example here I'm showing is for rubidium 87, where the transition is at 6.835 gigahertz. And then the light should be at 780 nanometers. And this device can impart a 1 radian. So this 1 radian is what alpha is. It can impart a 1 radian modulation depth if you drive it with 30 dBm of microwave power, which is 1 watt of power. And just for reference, that just means that you would convert this much, around 20% of the light to the first side jet, which is what you're trying to do. So what we've worked on in this group is a device that can do everything that device does. So electro-optically modulate or phase modulate light at a qubit transition frequency, but do it all on chip in a CMOS compatible platform, which the benefits of which have been discussed by Matt. And the problem is that silicon nitride and silicon dioxide and the other materials that are available to us in CMOS compatible foundries don't exhibit an electro-optic effect. So we have to get around that with a different modulation mechanism. And then the other problem is that depending on the structure that you're dealing with, the mechanical properties will vary. So for example, if you have a large structure like a table, the resonance frequencies of that table will be very low compared to the gigahertz frequencies of the qubit transitions. And even if you have like a small structure on a chip, like small to a human, like hundreds of microns by hundreds of microns, the resonance frequencies of that structure will also be much lower than that of the qubit transition frequencies. So what we've done is we've made a very small structure that is mechanically isolated from the rest of the chip. Like you can see in this schematic here that there's just air surrounding this little rectangle, and it's even undercut beneath it so that it's more or less floating over the substrate, but just supported by these periodically placed pillars. And that causes its mechanical resonance frequencies to be very high in the gigahertz range. And if we could excite a mechanical mode at one of those resonance frequencies, we would generate a lot of strain that's oscillating at a gigahertz frequency. And that strain would subsequently modify the refractive index of all of the materials that are undergoing the strain. And then if light was propagating through that oscillating strain, it would accumulate a sinusoidally varying phase, just like the electro-optic modulator. So here on the left, I'm showing one of the mechanical resonance modes of the device shown here on the right. This is just a freeze frame of it. Imagine it's just sort of oscillating inward and outwardly and doing crazy stuff really, but it's varying sinusoidally. And then on the just below it is the optical mode that would be supported by a waveguide that's within this mechanical resonance structure. And that's showing how the mode propagates through the mechanical mode along the z-axis. The structure is about 1 micron wide, and it would have a length of around a couple millimeters. And just to put that into perspective, this more or less to scale those modes shown next to a human hair. So it's very small. And then this is a top-down view of the actual fabricated device. We would put light in here, it would travel along the waveguide, and then this part where the screen gets a little darker is where that etch has been made so that the structure is mechanically isolated from the rest of the die. And so we made these devices, and then this is a slide on how we tested them. So the main principle to understand is that if you have two different laser fields that are oscillating at two distinct frequencies, omega 1 and omega 2, and you combine them together and measure their signal with a photodetector, what you measure is the intensity, then you get a signal that oscillates at their difference frequency, delta omega. And normally it's not such an observable phenomenon if these two light fields have vastly different frequencies, like for example, red and blue light. If you add them together and then try and measure this oscillating frequency, you would need a detector that can measure signal like once every femtosecond, which does not exist. So, but if these frequencies differ by gigahertz frequencies, as in the case of this device, then you can actually buy a photodetector that can measure the strength of the signal at this difference frequency, which would be at a gigahertz level. So what we do to test the device is we send a laser into fiber, we split it into two paths. One of the paths goes to the chip where it gets sinusoidally phase modulated, as I've discussed, which creates all of these new frequencies at those Bessel function weighted sidebands. Those new frequencies come out of the chip, and then we combine them with the light that never went into the chip at the photodetector and create a bunch of these difference frequency signals, which we can measure with some electronic equipment. And this plot shows, after going through that data, how much power there is at the original frequency, the first sideband, and the second sideband, as a function of the frequency at which we drive the device. So you can see, like, at certain frequencies, this is peaked. So here, of course, the frequency labels got moved around somehow, but this would be around 1 gigahertz, and this peak would be around 2.3 gigahertz. And at those peaks are frequencies at which there's a mechanical resonance, and therefore at which strain is enhanced by the Q factor of those resonances. And so we get much stronger modulation. And to convert that into modulation depth, you can just sort of mathematically analyze that data and convert it into a modulation depth that's shown on this plot. And what we find is that the modulation depth at that 2.3 gigahertz mechanical resonance exceeds 2 radians with just a 15 milliwatt driving power. And this takes place for a 737 nanometer light. And as I mentioned, at the modulation is at 2.3 gigahertz. And just to compare that to the commercially available device I previously discussed, that's twice the modulation depth with about 100 times less drive power at a similar wavelength and frequency. And of course, like on a CMOS fabricated integrated circuit. So I mentioned before that all this is for Raman control of atoms, and it turns out that the atom doesn't respond to just the mere presence of new frequency components at the separated from the carrier at a qubit transition frequency, but it responds to intensity modulation. It responds to the amount of intensity modulation that's at the qubit transition frequency. So that's summarized here in this equation that shows that the effective Rabi frequency, which is the rate at which that qubit will oscillate between the ground state and the excited state, is proportional to this sum, where this sum is saying that imagine you had a frequency comb where each comb line was separated by the qubit transition frequency. The effective Rabi frequency would be the sum of the product of neighboring comb lines. So all that's to say is just that that's the amount of intensity modulation at the qubit transition frequency. You might expect that by generating these new frequency components with sinusoidal phase modulation that we actually do create intensity modulation. But if you look at this equation here, you definitely don't, because to calculate the intensity, we just multiply the electric field by its own complex conjugate. And since the electric field, the only thing about the electric field that's been modified is its phase, that's obviously not, that's just going to be constant. However, if you actually look at sort of the frequency components of the phase modulated field, it's kind of surprising that you don't create any intensity modulation, because, for example, if you look at this carrier signal and its neighbor, this purple first sideband, those two should, just as I discussed in this measurement slide, those two should make some intensity modulation at their difference frequency, which is the qubit transition frequency in this case. And in fact, they do, but as I'll show in a second, that it perfectly cancels out with other intensity modulation produced by adjacent sidebands. So this equation shows the intensity signal as calculated from the frequency domain picture of the phase modulated field. And let's just zoom in on this term here that's oscillating at the modulation frequency. So as I mentioned, this carrier and the first sideband will beat together to create intensity modulation. However, so does the carrier and the negative first sideband, which is this term. And similarly, the first sideband and the second sideband beat together, the negative first sideband and the negative second sideband beat together. And it turns out that all of these added together is exactly 0. And that's because there's a property of Bessel functions that J-1 is equal to J1, but multiplied by -1. And that's for all of the odd order Bessel functions. So this term would just become J0, J1 with a negative sign out in front. So these two would cancel out to 0. Similarly, this one would get a negative sign out front. These two would cancel 0. So they all add up to 0. Long story short. But this can actually offer us a clue about how to convert the phase modulation to intensity modulation. Because, for example, if this term here just was somehow plucked out and disappeared, then this term here would have nothing with which to cancel, and then there would be non-zero intensity modulation at the qubit transition frequency, which is what you want to drive Raman transitions. So how to pluck out this term without modifying the rest of the field? So we've already discussed ring resonators, but I'll just give a quick reminder that they can act as very good filters. The transmission as a function of frequency could look something like this. So that if you passed light through a waveguide by one of these ring resonators and it had this frequency here at the dip, then none of it would be transmitted and therefore it would just be filtered out. But other frequencies nearby would not be filtered out, they would be transmitted through. So here is an example of a device that could create intensity modulation at the qubit transition frequency for Raman control. We first start with light coming in from the left here into one of our phase modulators I've discussed. We produce sidebands on that carrier. And then, like I mentioned, we want to remove one of them so that the intensity modulation no longer perfectly cancels with itself. So then we have a ring here that we would pass the light by to filter out one of these components, in this case the orange component, and now the red and the purple sideband can beat to create non-zero intensity modulation. So that's one scheme. Here's another cool scheme where light comes in from the left, passes through a phase modulator, gets its sidebands. Now these rings are no longer just with a single bus waveguide, but a bus waveguide above. And what that does is the component which the ring filters out no longer just disappears from the system. It is transmitted through to the waveguide above. So we'll filter out the orange component here, filter out the purple component with the second ring, because they would, in this scheme, be set to have different resonance frequencies. And then those components that got filtered out will now be propagating leftward in this bus waveguide above. So the purple one would get filtered through this ring and start propagating left, where it'll encounter the orange sideband that got filtered out here. And then those will beat together to create intensity modulation at the qubit transition frequency. And then the cool thing about this scheme is it allows us to put a tunable phase shifter between the two sidebands that eventually meet to interferometrically beat. And what that allows you to do is do arbitrary qubit rotations on the block, single qubit rotations on the Bloch sphere. Because without this phase control, you would just be stuck on one great circle around the Bloch sphere, and this allows you to move along any great circle. Then there's a third option that you put these phase modulators into an interferometer, and I won't go into the details, but that also allows you to convert the phase modulation to intensity modulation. And yeah, that's it.
All right. Well, we have about 7 minutes left, so I think that'll probably conclude the formal presentation, but I would be happy to take questions from now until then. So if you have any questions, yeah, please type them into the Q&A. Hope that you enjoyed the presentations and learned something. If you would like to learn more, actually, I teach a class that is available online through the College of Optical Sciences here. You could enroll in that class. It starts, if you really wanted, you could start this spring. So just think maybe starting next week. I don't know exactly how complex it would be if you're not currently enrolled as an online student or something to take that class at U of A. But nevertheless, if you want to learn more about this stuff, I do teach a class on it, so you can figure out how to enroll in online classes. Could I share the course link? I don't know. Let's see. When you say a course link, yeah, I think maybe if you'd like to know more about the course, why don't you email me? My email is iconfield@arizona.edu, and I can get you that information, but I don't actually have a link offhand, and I think a link wouldn't necessarily give you what you need if you still need to enroll either. So I want to like get a little bit of background information from the Associate Dean for Graduate Education and answer your question properly. So, but yeah, email if you're interested in the class. Okay. Any other questions? Take your time. Some of the questions might be long to type, so sit here a few minutes.
As we have people exiting the course, please note that we have a post-course survey we would love to get your input on. When you exit Zoom, it should automatically direct you to that link. Please take a couple moments and give us your feedback. We greatly appreciate it and rely on that feedback to make changes to our courses.
I suppose this is relevant to us and everybody there, but I think that they post this, like after the course is done, they can still go and rewatch it, and they like to have all the slides for them. So can you guys send me the slides that you did today?
I will be giving out slides.
Okay.
That's too much.
Okay.
But yeah, you can rewatch if you'd like.
Okay.
I guess still have 28 participants in, so they've either left their computers open or they're all frantically typing questions. Great class, thanks. All right, that's the easiest question. You're welcome. All right, well, I think we'll probably shut it down. So thanks again to everybody who attended. Oh, wait. Here we go. Doped graphene methods in passing. Are they similar? How do they work? Let's see. So I'm not an expert on doped graphene, but generally you can you can dope a lattice. I would think doping graphene would be pretty hard because doping is one of, well, you can all hear me, I'll just answer. Graphene is one atomic layer thick, or if it's, bilayer graphene or something, maybe it's two, but it's very thin. The depth that our ions are implanted in the diamond is usually many tens of nanometers or even deeper, which is, hundreds of atomic layers. So I'm sure whatever methods that they use to dope graphene probably look substantially different. It wouldn't work to have like a very energetic beam of ions that that were just directed onto the surface. They probably use something more like a diffusion process, where you just use like hot atoms to kind of get enough kinetic energy to wander around and eventually find themselves in a lattice site, something like that. But I don't actually know. I had not heard of that, so I will probably read up on it now. Thanks for your question, though. Okay. Well, now I think I'll probably shut it down. Thanks again. Have a great day, everyone. Oh, yep, thank you. Thank you. It was very fun for me.